Hello. Good afternoon, everyone. We will now start the next session. Hope you all had a delightful lunch in the afternoon. After very insightful panel discussions before lunch, now I am pleased to welcome you all for the next session, next technical session one, that is on challenges in green hydrogen production. Sri Anant Pandey, Chief Manufacturing Officer of Deepak Nitrite Limited, was supposed to chair this technical session. However, due to a medical emergency, he is not able to join this event in the last moment. So we have to have a new chair. So we tried with various other experts, but finally we have to pressurize Dr. R. Venugopal sir, as sir for this session as well, because this is a technically very important session. So please join me again to welcome Sri Dr. R. Venugopal, IPSS, Joint Chief Controller of Explosive PESO, to chair this session also. I request Ms. Maitri Nayak to welcome the guest with sapling. Thank you, Maitri. Sir, now the floor is yours for the first technical session on challenges in green hydrogen production. Thank you.
Sorry to be here in another one more session because certain things are not in our hands. Distinguished delegates, speakers, and chairs of various sessions who are assembling here. This is a very important session, challenges in the green hydrogen production. When we are planning this session, we thought about who are the manufacturers of hydrogen. Then we went to the Deepak Nitrite and selected the chairman for that. It's my privilege to invite Sri Srish Androlia, the Vice President and Head Operation of L&D Electrolyzer Manufacturing Company, to be here. Please welcome him to this session. Mr. Srish Androlia will be giving the keynote address. Now I request Rennie Andrew, Deputy General Manager of Bharat Petroleum Corporation, to be here. Rennie, please. Yes, please be seated, Rennie. Mr. Shaji John, the Senior Vice President. Homium, please. Shaji. Welcome. Pavan Mendrita. Pavan, please come. He is the head green hydrogen of New Energy Thermax Limited. Welcome, Mr. Pavan. Yeah. Thank you, Avani Nathani, Jivani Patel and Hemali Salvadia and Niyati Parmar for honoring the panel members today. So this is now the first keynote address in this session is by Shirish Antolia, the Vice President and Head of Operation of L&D Electrolyzer Manufacturing. I have met Mr. Shirish when I visited the first of the green hydrogen installation at their premises at Surat. So when we meet any person, when we are discussing some issues, we understand his capability. How he is subject-wise thorough enough to discuss matters. So that day he has noted, I visited his plant to see the first green hydrogen electrolyzer manufacturing plant in the country. Shirish is having a 32 years of experience at various L&T group of companies. He is the project management leader in technology absorption, in indigenization, procurement, erection, commissioning, power plants, cement plants, and of course, he is in a scheduling the international market meetings, cost, quality, safety, productivity, and all the average project cost he had done is more than 500 crores. He has been successfully developed a joint venture between L&T and MHI for ultra supercritical boiler pressure pots, pulverizer and heavy casting unit for domestic and international market. As ultra supercritical boiler factory head, he led establishing world-class factory, global center for manufacturing with operational excellence in digitalization, strategic and synergetic team building. As a member of L&T Green Business, he contributed for green hydrogen strategy, identified in advance huge potential for hydrogen as next green fuel and studied multiple electrolyzer technology. He has established the electrolyzers business strategy, technology identifications, business plan, manufacturing setup, team building for supply of electrolyzer in domestic and export market. He is now the project director for India's first green hydrogen project with blended fuel firing, executing 1 gigawatt manufacturing setup with highly automated assembly and testing line. Let all of you join me with a clap inviting Mr. Shirish Antolia for the keynote address.
Good afternoon, everybody. On behalf of L&T Green Tech, I thank Peso and Dr. Venugopal. Actually, Dr. Venugopal personally called me and he was following up with me regularly that I must join this forum, though there are other businesses what I was doing. So thank you very much for inviting and giving the opportunity to L&T to present our case. As has been explained by him, L&T is far front in manufacturing and in green hydrogen as a part of our ESG goals. Management has thought a long back that how to work towards sustainability, and the green hydrogen was one of the foremost area that they had in their mind. So I will take you through some of the features of our technology and what we are planning, and then having your question and answers. So as everybody knows, Larsen & Toubro is a giant conglomerate with a turnover of 22 billion and today's market cap of about अच्छा इसमें है हाँ okay. We have market cap of about 60 billion. This is a little older figure right now, and the CRISIL rating of AAA. Very widely known company with a lot of potentials in various domains. As we'll go further. Next. Yeah, this is our global footprint. Approximately 50,000 workforce working all over the world, and about workmen of about 4 lakh workforce working at various project sites. This is the major business structure, as you may be knowing, the EPC projects, which are on the infrastructure, major infrastructure projects within India and outside India are being done by L&T. On the energy front, we have like on the all kind of facets of energy covering coal, gas, nuclear, renewable, and the area which I come from now, working on green manufacturing and development, wherein we are looking at the green business. Manufacturing, we have a major manufacturing facility at Hazira, as you all know, in Surat, covering about 13 ICs of heavy engineering, pressure vessels, heat exchangers, of nuclear reactors, power plant equipments, forging, large forgings, turbines, boilers, and offshore platforms. And now we have started electrolyzer manufacturing also. Another on the services front, we have on the, as you know, that LTI Mindtree and LTTS. So there's the biggest, I mean, the big contribution for infrastructure and energy business, and other contribution is coming from financial services. So this is our sustainability goals. As you may know, that we target to become water neutral by 2035 and carbon neutral by 2040 as a company. And some of the area which we are target working with the renewable energy usage in the companies at various premises, how to reduce the energy intensity, water intensity, and recycle use of material. Safety is the paramount at all our sites. We are trying to bring the workforce to the updated safety levels, and also from the point of view of digitalization, using the highest level of AI and digitalization in the safety in various sites, as well as hydrogen, as you may we discussed in the morning, that being quite volatile and is under pressure. So a lot of aspects of fire and gas detection, hydrogen detector, firefighting, clean agent system, all those are being developed and considered in our various hydrogen projects. So safety has been always on the front. Now we'll take you through our manufacturing and development on the green specifically, which we have been working on last 2 years. So this is the major structure. We have one is the development arm, which is green hydrogen for India, GH for India. This is a joint venture between IOCL, L&T, and Renew Power, which will be bidding and building the development, the hydrogen projects at various sites, primarily at refinery and fertilizer plants, as the green hydrogen will be the major fuel. As you all know that IOCL has a major hydrogen usage in the refinery, and about 700 KTPA is the hydrogen quantity what we are talking. Out of 700 today, only about 1.5%, that is 10 KTPA, is what we are saying that in IOCL Panipat we are going to change. So there is a project which is under discussion now, and that is where the green hydrogen will be produced together, and it will be used in our refinery operation. So that is where the various development projects within India, outside India also. We are also bidding for multiple European projects for hydrogen and ammonia, green ammonia supply. And the next business is on the EPC front. So apart from developer and owner driven, we will have a EPC business also, which will be doing projects for various customers to put up their green hydrogen plant or ammonia plant. And the third one is the one where I'm coming from, is the L&T electrolyzer manufacturing. L&T electrolyzer manufacturing is a separate entity has been created, and presently in Hazira, as a part of our green transition from coal to green, in our turbine factory, some of the bays we are developing and using them as our factory establishment. So we have already ready-made factory available with the crane and all the facilities also to a great extent, but we are improvising, we are modifying it for our requirement of electrolyzer. So this is the Hazira factory. We are trying to show some of the factories in Hazira which are heavy engineering and nuclear reactor, turbine, boiler, forging, high pressure vessels. Some of the facilities in our Hazira. So we have a huge infrastructure available, huge front technology available, workforce is available. I mean, and lot of cross-functional teams are there which understand each other and try to help each other and work together. So it's very easy to create a manufacturing infrastructure in Hazira. Now I will take you through the electrolyzer manufacturing. So as we mentioned in one of the forum, that we have done tie-up with technology license agreement with Mrs. McPhee. There is a French company, and they are in the high pressure alkaline electrolyzer. So we are, as a known and proven mature technology, we have targeted right now on alkaline electrolyzer that understand this technology, completely absorb the technology, and mastermind the manufacturing. So that is where we are putting all our efforts to build this alkaline electrolyzer indigenously, completely in India and in mass production way. So this is the typical the diagram of the electrolyzer, wherein so if you see the we have shown here the stacks. This is one stack of 0.5 megawatt, and it could be of 4 megawatt at later date, and that makes about 1.5 megawatt gives about 100 normal meter cube per hour of hydrogen. So this makes about 400 normal meter cube per hour, which will be corresponds to about if you say divided by 10, about 40 kg per hour, something like. And this is next to it is electrolyzer processing unit, wherein the hydrogen and oxygen is separated through various equipments covering heat exchangers, pumps, coolers, and the final output of 24 about 25 bar pressure, hydrogen and oxygen both are available. So this is a typical stack construction for alkaline electrolyzer. It consists of primarily three things: anode, cathode, and bipolar plate. These are the three major components of the any electrolyzer stack, and they are mounted on a cell frame concept called holding plate. So we have indigenized now all these components. They consist of carbon steel or stainless steel components, or some of the things are injection molded. So all those technology has been understood. The material has been understood. We have made it already components, all of them. And now it's almost that we are creating our factory parallelly and also having a supply chain for all these components. And then we'll be starting assembling very soon. Partly it has been assembled already. One or two stacks has been assembled. But basically from September, we are saying that we'll be able to produce in the mass scale at least minimum about 100 to 150 megawatt in the beginning. And after the stack are also tested pneumatically and with hydro also. There's a pneumatically also they are tested with the nitrogen pressure, nitrogen and helium. So they are tested about at least at around 43 bars. So these are all pressure tested. So this is the typical testing station what we have. After the stack is assembled, then it will be going through a full functional test of the full production capacity. So it will be applied with the voltage and current, And we have a complete setup. We are creating a full-fledged shop with the testing facility and all the utilities like demean water, compressed air, nitrogen, and all the relevant power requirement, transformer, rectifier, and there is a control room which will be controlling operation of the stack, and we'll be running it for about at least 10 to 12 hours, wherein we'll be testing and checking all the parameters of it. Basically, it will be polarization curves will be created for the voltage and current, which will show the efficiency of the stack. So this is the one plant what we have created. We said we declared in February, we had assembled it. And on 1st of March, we have declared this is commissioned. This one electrolyzer processing unit left side is there. And on the right side, we have two stacks, which is equivalent to 1 megawatt, 0.5 each. And these were assembled and it has been run for the full production. And it has been proven successfully without any problem. Yeah, this is the, can you start the video, Jara? Video voice?
Stack and its processing unit at world-class manufacturing facility in Hajira, and the same has been installed and successfully commissioned at the existing green hydrogen plant. The electrolyzer stack components like anode and cathode electrodes, separation plates, cell frames, membrane retainers, pressure rings, O-rings, end plates, tie rods, base frames have been manufactured, assembled and tested at L&T manufacturing facility. The electrolyzer processing unit components like hydrogen and oxygen gas separator tanks, gas coolers, condensers, gas analyzers, heat exchangers, electrolyte circulation pumps, instrumentations, venting system have been manufactured, assembled and tested at L&T manufacturing facility. The 1 megawatt system consists of two electrolyzer stacks of 500 kilowatts capacity each, where water is split into its constituents, hydrogen and oxygen gases in an alkaline medium. The purity of these gases produced through electrolysis is continuously monitored using the gas analyzer system. At its rated capacity, the electrolyzer module shall produce 200 nm3/H of 99.7% pure hydrogen gas at stack level. This milestone serves as a testimony to the design and L&T's capability to indigenize and scale up this technology for large-scale commercial manufacturing.
So this is, we have put in what Mr. Dr. Venugopal mentioned, that we had created first a green hydrogen plant to demonstrate the blending of hydrogen with the natural gas. That was in August 22, we had inaugurated and commissioned. And there also we had additional space. So we had already infrastructure available with the water and nitrogen and air and all those things. And also the power, solar power was available. So using that power, we had installed a transformer and rectifier suitable for this requirement. And then this was completely run and tested. So still now also we are trying various operations and all those things. So operation is going on. But basically idea is that okay, we have understood this technology and we are in a full scale mode to manufacture and indigenize it completely. Thank you. Any questions? I mean.
L&T is having the first green hydrogen storage. And you are going to manufacture the first electrolyzer in the country, even though it is with a foreign understanding. I would like to ask you, what are the current challenges in the hydrogen storage and transportation, and how this can be addressed?
Okay, I mean, that area is not my little expertise. Hydrogen storage is like what we are talking is the basically we are talking of ammonia then, because storage point of view, of course, we have not applied our mind right now, as you have said in the like if you say retailing, then retailing wise, what we want to store or how we want to store it and then distribute and all those things. Right now, our effort is on the electrolyzer manufacturing and producing the capacity.
But you had a plan, but you have a storage there, right?
That is different. That
Ah.
storage is only for the feeding to our furnace
Okay.
because it's a solar power. So
It
we
is a
have
solar power
available
one,
is only
which
one.
you are storing in a, how many metric ton kg tank
That
is
is
that?
a 20 meter cube. It's a small 20 meter cube two vessel at about 25 bar. So
Okay.
basically, it's like because we have a
It's a
solar
buffer
power for
vessel.
the one shift. So for balance two shift, we have storage hydrogen in the
Okay.
vessel.
So you didn't find any difficulty in that storage?
No, I mean we don't. I mean there is a indeed. I mean we have also that as you have seen that we have covered everything and all the safety and all those things ensured, and there are no issues. We have enough safety in the sense of safety relief valve above the vessels and other control mechanism. There are control valves after the when we are giving it to gas metering station where there is a blending happening. So there is a control before that, and so there are no issues has been observed so far.
What are the current limitations of the electrolyzer technology in terms of efficiency, durability, and cost? What are the current limitations of electrolyzers?
I would not say limitation. I would say the challenges.
Yeah.
Mainly like as the technology is not fully available. It is just coming now to because even in the Europe and US and all those places also they are developing. It is not that it is already developed and people have used so many places and all those things and then we are getting the technology. So parallelly we are also learning and developing. As Derek Shah said in the morning, like electrodes and cathode anode, when we are manufacturing, we have to also test it. I mean, from small scale, there are testing like L0, L1, L2, L3, L4. So L0 means you take 1 centimeter by 1 centimeter sample and test it. Then you make it 200 by 200. Then you make it 500 dia. Then you make it 800 dia. So there are the stages through which we have to go through. So those are the challenges. So we should have set up for those testing so that we can do faster and multiple testing for the long duration. And those once component proven and developed, then the efficiency further improvement will be the next phase. I mean, presently, of course, it will be at the efficiency what we are talking, but then the more coatings can be developed, indigenous coatings, which will give the better efficiency.
Okay. So you are telling that for the electrolyzer, so many youngsters are here.
Yeah.
Can you tell me what is the market integration and investment opportunities coming up in the renewable energy sector? How do you anticipate the challenges for economical potential and the benefits for the sustainable hydrogen economy? What is your advice for the youngsters who are sitting here?
No, I keep saying a team. I mean, like today, when we say that today we are starting hydrogen,
Yeah.
it's a hydrogen as a fuel, as we know that at this, okay, we are starting, but it is the challenge which youngster can have it more better in the sense that as we know that there are so many products from both manufacturing angle and from the technology point of view. Multiple technologies has to be developed, and those components needs multiple developments, analysis, engineering, manufacturing technology. So those are the things which are there available for youngsters. Indeed, that's what we are saying, that we have, like, you know, when we are talking about R&D, so we have young people, about 20-30 people are working right now on the shop floor, on the lab. So that is like working in the real life and then executing it and seeing. So that will be the like those are the things which we'll be creating on our India. In India, we will be creating those technologies.
So one, in my presentation, you would see especially the youngsters. What I have tried to cover in my presentation are what are the various technology challenges we have in different electrolyzers. And there are many, 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 many challenges. Some examples I have brought out. I think the field of electrolyzers is in a very initial stage now, very, very initial stage now. People have not run electrolyzers for, let's say, 20,000 hours or 4 years, 5 years, 6 years. I have given one example of a installation in China where they can't go below 50% load actually because of certain issues with the membranes and certain issues with the technology. So there are many challenges. And I think right now is the right time for, people who want to really get into technology, innovation, R&D. Hydrogen electrolyzers, fuel cells is one area where they should definitely jump into it. And, also we find challenges to find the right people today. At Thermax, I started the green hydrogen business about a year back. I cannot tell you what kind of challenges we had to find the right kind of people with right skill sets. Organizations are willing to, go to any length to get the right kind of talent and right kind of expertise in green hydrogen. So if you are developing that, it will be a great thing.
Sirish, for
Yeah.
giving a overview of the current challenges in hydrogen production, emphasizing the role of L&D's electrolyzer manufacturing and addressing these challenges. Please be seated.
Thank you. Thank you.
After each of these presentation, we will open to the delegates. Next is the presentation by Dr. Rennie Andrew. He will be sharing insight into the latest development of electrolyzer process, challenges faced, and potential solutions. May I introduce Mr. Rennie Andrew from Kerala, from Thrissur. Many of these people are Keralites. He has done his PhD in chemical engineering from University of Petroleum and Energy, Dehradun, Masters in Chemical Engineering from Indian Institute of Technology, Indian Institute of Chemical Technology from UDCT, Bombay, and BTech from Government Engineering College, Thrissur. His area of research include alternate energy technologies, green hydrogen, solid state metal hydrate based on hydrogen purification and storage. He has an experience on solar PV generation system, bio ATF production, compact thermal swing absorption, enhanced steam methane reforming. And he had so much of works done as a professional in Indian and international scientific bodies, research institute. He had more than 15 international publications. And do you know, he had 6 national patents, presented several research works on hydrogen as automotive fuel. You have an automotive fuel station?
No, we
BPC.
have building. Yeah.
Yeah. That is it. And he is every time he is presenting his papers in refinery technology meet, and he has got his best paper award in the steam gasification of biomass in the 5th SDM conference in 2050. Had been a publication in various conferences, Hydrogen and Fuel Conference, Global Pipeline Technology Development, National Team Meeting on Hydrogen Energy and Technology. Please welcome Dr. Rennie Andrew.
Thank you. Thank you, sir. So very good afternoon, respected chair, esteemed panel, and distinguished delegates across the industry. It gives me immense pleasure to stand here and talk about the favorite field, green hydrogen, the challenges, technology development initiatives, and the R&D scope in the area of green hydrogen. First of all, I would like to thank the organizers, PESO, IIChE, and IOCL Baroda, especially Dr. Venugopal, for giving me this platform. And on behalf of BPCL, I thank the organizers. So, it's not moving. Thank you. So the content of my presentation goes like this. So I'll be talking briefly about the perspective from the refining industry, because we are the refueling industry. the vision of green hydrogen, the country's vision, company's vision, the value chain, what are the challenges faced by green hydrogen production, then BPCL initiatives and the R&D scope which is there in this particular field. So the transportation sector has revolutionized our lives in the 21st century. And although the oil and gas is an indispensable component in our lives, we know that the emissions from this oil and gas is leading to the effects, like detrimental effects on human beings and environment. And the environmental conscience and the norms, the stringent norms which are coming, has created this kind of impetus for development of new technologies, sustainable technologies like green hydrogen and carbon capture and utilization. So if you look at the refinery, there are three segments. You can see that emissions are coming from the power and steam, the hydrogen generation, the SMRs, where we are generating hydrogen from natural gas, the refinery fuels like your naphtha and your fuel gases and coke. These are the emission points from refinery. So we have taken strategic steps to curtail these emissions, step-by-step conversion or switching from grid power to renewable power, switching from gray hydrogen to green hydrogen, replacement of your FO and fuel gases with natural gas, carbon capture, efficiency enhancement measures in the process units and conversion systems, and also securing carbon credits. So these are the pillars which as a company, BPCL is working towards to achieve this net zero goal by 2040. So this already we know that our country is focusing on this particular vision, the three pillars like energy independence, decarbonization, and advancing the economy by leveraging on the Atmanirbhar Bharat and exporting energy to countries and aligning with this vision. We have done a lot of analysis on the value chain of green hydrogen. What are the components which contributes to the success of green hydrogen economy? So first and foremost, it's the renewable power, water, the electrolyzers, hydrogen storage and transportation, and the use cases. So the early adopters like refineries, steel and power plant and fertilizers are going to be the beneficiaries in the initial stage, petrochemical industries, then blending of hydrogen and natural gas. We had discussions about this particular area. This is also going to be an early adopter in the initial phase. And moving further, the IC engines, fuel cell vehicles, heavy duty transports and all. And there is another small segment called utility power or the microgrids that are going to be another area of green hydrogen application. So I would like to come to the subject of discussion now. What are the challenges faced in the green hydrogen area as far as the production of green hydrogen is concerned? So I have listed out few points here. The first and foremost is the renewable energy economics, reuse of water for electrolyzers, electrolyzer cost and manufacturing materials, electrolyzer efficiency, skill development and training, manufacturing readiness, which our colleague from L&T has already talked about, the cost of the peripheral systems, these are also very important, and policies and frameworks and all the safety standards which are to be mandated for green hydrogen use. So I'll take one by one as a case. So we know that renewable power, cost of renewable power is the costliest commodity as far as the hydrogen production is concerned. So we know that the use points or the consumption points and hydrogen generation points and the RE generation points, these are all mostly located very far. So this kind of delinking has created a problem in getting the cost of hydrogen very low. So if you can see the right hand side of the slide, the OPEX and CAPEX split up, you can see that about 75% of the cost is coming from the OPEX, that is mostly from the renewable power. So what is the solution for it actually? As of now, the companies like BPCL, we have got something like 100 megawatt of renewable power established at various parts of the country. And we are also looking to establish something like 100 megawatt of wind power in Maharashtra and Madhya Pradesh, and another 52 megawatt of solar power is coming up in Prayagraj. And our aim is to achieve something like 10 gigawatt by 2030. So this renewable ramping up of renewable capacities are going to happen. So along with this, the green hydrogen infrastructure, the production of green hydrogen infrastructure also had to take place. So what are the mechanisms? One mechanism which we can highlight here is the hybridization of the primary energy sources. That is what your PV, photovoltaic solar systems with and without battery systems, wind turbine systems, offshore, onshore. The capacity factors individually for each of these primary sources are widely varying. Cost is also widely varying. So what is the solution? Hybridization will be able to finally push your capacity factors towards maximum, like 80%, 90%. Cost also should be coming down. So this is, again, depending upon the location, weather conditions, we need to co-locate these hybrid RE power sources and electrolyzer plants and consumption points. That is one solution which we are looking at to see that green hydrogen going to be a viable solution in the future. Second problem, that is reuse of water for electrolysis. As we have seen that when you're talking about water, water is the most important commodity for production of hydrogen through electrolysis. So one factor which I wanted to define here, that is the water footprint. So most of the hydrogen developers, green hydrogen developers, use water from the available resources, that is a clean or surface water which is available. But when you look at large infrastructure like refineries, we know that normally for any treatment plant, like your water treatment plant or the DM water plant, these are all common facilities, shared facilities within the refinery, which are large in capacity. So ultimately your cost of water goes down. So you can achieve the bottom line cost of water. So this is one strategy which we need to adopt. And we also have to consider now for green hydrogen producers, some kind of provisions have to come to utilize the MLW, the wastewater, ETP water, or your saline water to be converted into the electrolyzer grade water. So the one alkaline electrolyzer requires very pure water, ultra pure water of conductivity less than 1 microsiemens per centimeter. So these are the kind of activities which someone has to do actually, and we are also geared up for this, taking up the areas where you have the wastewater which is available, converted to electrolysis grade water. And it is also important that the green hydrogen producers have to do a water scarcity mapping. And if you compare the water electrolysis with the natural gas reforming systems, you can always see that in the table below, you can see that if you compare a solar and a wind, your water at the source which is required is very, very less per ton of hydrogen produced in the case of wind. Whereas in natural gas also, when you're processing the natural gas, you require a lot of water. So if you scan the complete supply chain, starting from the source of the water till the end of it, actually, we call it as the well to gate. If you do that analysis, we understand that the total water footprint for the wind-based systems or the renewable-based systems through electrolysis is going to be lower than the conventional fossil fuel-based systems. So one has to keep doing this kind of activities, that how this water circularity can be achieved. So that is the main factor which is going to come in the near future. Coming to the electrolyzer manufacturing, the manufacturing materials and processes that already our colleague from L&T has mentioned about this. What are the various there are different type of alkaline electrolyzer. If you take one electrolyzer technology, that is alkaline electrolyzer technology, which is the matured one. If you take that technology itself, there are wide variety of configurations available, varying widely in terms of cost, performance, and durability, life. So if you take a simple example of the Chinese or Southeast Asian electrolyzers, that's the carbon steel bipolar plate. They actually coat it with nickel through electroplating. Then they already use the perforated nickel mesh as electrode. So if you compare this with the advanced technologies that we consider that the technology which we are working with, Bhabha Atomic Research Center has developed an alkaline electrolyzer technology which is very robust. So we use SSI bipolar plates and nickel electrodes. Basically, it's a porous, highly sintered electrode which is stable for years, 10, 15 years. So one has to look at each and every components, and zircon membrane which is used inside the electrolyzer that is imported currently. So the ecosystem needs to get developed in India. The gaskets made out of polymers through injection molding. So these are the components which are there in the electrolyzer cell, which is assembled and stacked and encapped with carbon steel flanges. So this is a basic configuration of the electrolyzer. So I would like to take your attention to one important factor, that is the raw material, which is playing a big role in India, because we know that we don't have much resources of this kind of materials. So if you compare the major components, the zircon I'm eliminating, it's a membrane which is actually imported from outside. Carbon steel, the cost of carbon steel which is utilized in 1 kilowatt of electrolyzer, that we already get from the literature, and we know our figures that what is the SS materials that is going in the electrolyzer stack. So based on that, you can calculate. So if you take an average figure, the cost of raw material itself is coming something like 10,000 rupees per kilowatt. That's nearly 1 crore per megawatt. So what India has to do, that we have to tap in the resources. What are the sources of nickel which is available in India? What are who are the bulk suppliers? So this is something which we need to do as an exercise to bulk up the raw material availability in India and work towards a bottom line figure. Another important thing that he has already mentioned about the processes that being adopted in the electrolyzer manufacturing. The bipolar plates are normally made through laser cutting, stamping methods, or by machining techniques. Nickel electrodes, which are made through sintering process or by coating, electrocoating. So these are various value chains which are available. People are talking about gigawatt factories. So in Europe, we could see one particular phenomena that they call it as cluster manufacturing. So for each of these components, there are different manufacturing lines. People, if somebody is working on electrodes, he may not be working on bipolar plates. They make only electrodes. So this kind of manufacturing ecosystem has to be developed in India. So as BPCL, we are working with few manufacturing partners who develops all these each and every component, so that we can beat the scale of manufacturing or the cost which is achieved by Southeast Asian countries by doing this kind of approach, because we may not be able to meet the scale, gigawatt scale, but at least through this approach, we will be able to reduce the cost and achieve the bottom line. Can you move the next slide? Yeah. So next important factor, that is the efficiency. So from the exercise that we have been doing with BRC, we realized that the technology has to undergo development pathway, that there is always a learning curve. Mr. Shirish also has pointed out this fact, that with making one prototype is not going to be the end of the road actually. So you have to try different combinations to achieve the efficiency. So we are working on various fronts, primarily in 3 areas, that is to increase the activity of the catalyst, having some dopants in the electrodes, improve the mechanical strength of the catalyst layers, increase the operating pressure of the electrolyzer by trying different type of membranes, reduce the ohmic losses by reducing the interfaces, resistances, and by using thinner membranes. So you have to have different kind of what you call membranes to do all these things. So this is a kind of an R&D exercise which has to undergo, and that we at BPCL R&D, we have set up a state-of-the-art laboratory for doing all these studies. So we are carrying out this. Although the first commercial prototype of 500 kilowatt is going to be ready in September, the activities, these kind of activities are going in parallel. So because this is this is a non-stopper, this should continue actually, so that ultimately, as you can right hand side, you can see the theoretical maximum efficiency. The current consumption is like 39.4 kilowatt hour per kg, and currently we are at most of the electrolyzer systems are at 47.5 to 55 kilowatt hour per kg, and the target efficiencies are like 42 kilowatt hour per kg. That is achievable if provided we progress in this fashion. Coming to skill development and training, that's a very important area. So whenever we are talking about the green projects, green hydrogen and renewable power projects, the social and economic infrastructure, basically they are not conducive for attracting skilled workforce. And training capacity limitations are also there in such regions where these renewable power projects are going on. Or the best practices which are adopted by the leading players globally, that is also not easily accessible. The industry volatility or the boom bust cycles, because today there is one project, but tomorrow there is no guarantee that whether the project will continue or not. So these kind of issues, and even there is an intense price competition happening in the market. So these are all issues by which the workforce from the adjacent industries are not able to move from their original field to the green hydrogen and power domains actually. Rapid mobilization of the workforce is happening because the timelines for our current projects are very tight. So people are not able to get that learning, or skill development happen in smooth fashion. So what is the solution? That industry and academia led programs, training programs, that is one pathway which is there already. The industry, the institutes like Fraunhofer are following this kind of approaches. And manufacturing readiness and on peripheral systems. So as our Mr. Shirish has also pointed out, this readiness is like you have to have a supply chain of materials, you have to have standardized manufacturing processes, cost-effective manufacturing processes, technology learning rate, that is very important actually. So every variant you make, that electrolyzer designs you make, you learn something, improve it further, and implement the same the next model. Capacity utilization. And another important thing which I want to touch upon is the peripheral systems that we are already finding as a problem now. So transformers and rectifiers that are used in the sense, there are a couple of manufacturers for rectifiers in India, but again, limited manufacturing is a problem. Hydrogen compressor, the major components like your crankcase, your diaphragm, etc., are imported. So we have to have to find solutions to manufacture these components in India. Water systems, electrolyte circulation pumps, cooling water systems, control systems, SCADA, long lead items, very expensive. Analyzers and hydrogen detectors. There are very limited manufacturers, and at the same time, the cost is very high now. So these are some of the levers that people can work on. Now, last but not the least, the policies and frameworks for mandated hydrogen use. So we know that there are mandates coming up for refineries, but again, it is taking time to implement this in the field. Although the hydrogen blending in natural gas is taking momentum, it also has to move towards the automobile sector also. Then the viability gap funding for green hydrogen projects. So already MNRE and IRA are working on these kind of schemes for mobility sector. Support from states for converting the public transport systems for HCNG and hydrogen, pure hydrogen. Rationalization of road taxes, subsidize in promoting the manufacturing of the vehicles. So these are some of the levers that which one should be working on. Coming to the BPCL initiatives, BPCL has a big presence in the natural gas market. We have got something like 35% market share in the gas business, about 52 CGD locations. We are trying to put this blending of hydrogen and natural gas networks in our CGD locations. Progressively start the blending from low percentage to 20%. BPCL Bina Refinery has put up a 5 megawatt green hydrogen plant. The hydrogen dispensing station is being put up. It's a greenfield location starting from solar to green hydrogen fueling infrastructure is going to be put up in Cochin International Airport, Kochi. Various collaborations are happening at the R&D front. I already talked about the BRC. A lot of evaluations are also pilot scale evaluations we are doing with different type of electrolyzer systems. Also, we are working on the metal hydride based hydrogen storage systems and fuel cell system development. And last but not the least, the use case like your hydrogen in the domestic and commercial sector, it is going to the burners. So we already have developed high efficiency burners for LPG and PNG applications, 74% highest ever reported in the country. So similar way, we are going to also develop hydrogen burners for hydrogen and hydrogen blended natural gas. So these are some of the areas where I already touched a few points that you working on different type of catalyst materials for electrodes. Also develop anodes for AEM electrolysis, membranes for high pressure alkaline electrolyzer systems, ceramic composite membranes for high electrolysis. So wherever we have our in-house strength, we are doing internally. Otherwise, we are tying up with institutes, academic institutes. And it is also important to develop the hydrogen mobility infrastructure. So we are tying up with few auto
Rani?
OEMs for that.
Time shortly.
So
Yeah.
this is my last slide.
Yeah.
So thank you so much, sir. Thank you so much. And if you have any questions, I will be happy.
Dr. Rani, it was been a wonderful session. You have covered the entire aspects of insights into the latest development in electrolysis process, the challenges faced and potential solutions also you have told about. Where should research and development efforts be found to address the current challenges in green hydrogen potential?
No, as I told that now, if you're talking about the electrolyzer architecture,
Yeah,
we are not very far behind the Europeans because
Excellent.
all these studies which I have shown,
Yes.
R&D scope, it is
give BPC a big hand because they have done a very good work in research.
so it is few miles away to achieve the epitome of success. That's what I would say.
How can the collaboration between academia, industry and government to be improved? Do you have any suggestions for the acceleration of innovations?
Yeah, the academic institutes can work up to a certain level, actually. That we have seen. So from that level, if you want to commercialize or scale up and commercialize systems, you have to have some kind of standardized methodologies. You have to have this scalable manufacturing methods to be developed in parallel to the lab scale developments, because the theoretical efficiencies can be predicted from a lab scale system, but the actual efficiencies, the actual prototypes have to be developed at industries and to be tested actually. So this is the work for industries. Academy, let them do that work actually, that, okay, what is maximum possible theoretical efficiencies or what is possible at lab scale, but it is a duty of the industry to take it forward and do the scale up studies.
One important fact I have seen that the periphery systems, you were talking about I request all the youngsters here, think about this. When the electrolyzer manufacturing companies are coming up, the periphery system has to be strengthened. That's what he was talking on, transformer, H2 compressor, RO. These are all the things we were discussing. It's a very, very important point. How the works are going on that field.
Right now, if you frankly speaking, the activities which are going on only at silos, actually.
Right.
That is a problem actually, because if you're talking about rectifiers also, there are few manufacturers who make it.
Absolutely.
But if you are changing the specifications of the electrolyzer itself, they also have to fine tune it. This is a problem. So the things has to go hand in hand actually.
Thank you, Rene. We will have discussions later on.
Thank you, sir.
Can I call upon Shaji John? He is from Ohmium. He will discuss us the manufacturing process of electrolysis, testing methods, and how they impact green hydrogen production. Mr. Shaji is an electrical engineering from NIT Bhopal. He is an executive MBA from SPJ in Mumbai, and he is a certified project management associate, IPMA Switzerland. As senior vice president of Ohmium, he is responsible for business development and sales of Ohmium Green Hydrogen Technology Company since June 22. In addition, he also leads the Global EPC and Development Initiative. He is a board member of Ohmium India operations and is a key player in landmark deals of Ohmium such as NTPC 400 megawatt green hydrogen projects, which are
काही केलं होतं बालू सरांना
most ambitious in the world. He also cultivates strong relationship and partnership with the leading global companies like Shell, Hero Futures, AMP Energy, and more. In his last assignment with L&D, Shaji John was responsible for developing renewable business and ensuring that L&D is well placed to capture considerable market share in the emerging clean energy space. The solar initiative was started under his leadership back in 2008 and reached portfolio of over 8 gigawatts of solar projects, 150 MW hour of battery energy storage systems, and 500 microgrids. He's a tiger, right? He was responsible for bagging one of the largest contract of NEOM green hydrogen project involving 3 GWP solar and 1.5 GW wind, 1.5 MW hour of batteries and associated grid management system. Let us welcome Sri Shaji John to this august audience. Shaji, carry on.
Thank you, sir, for that introduction. So, Dr. Venugopal Sahab has told about there are few Keralites here. So one is he, one is Reni, and one is me. But there is another coincidence that there are 3 L&Tites here. One is Sirish, and another is Pavan, and one is me. So that's I am the common man of being a Malayali as well as an L&Tite. Thank you. So the picture what you are seeing is our electrolyzer in real world, in real size. It is a 3.15 megawatt system, and it's installed nowhere else but in our Bangalore factory. Another important thing is that Time Magazine has rated us at the top of the category in America for the technology which we have developed. So that is Ohmium. Just to give a glimpse of what market is going to be there in the days to come, like youngsters are here and they would like to see that what kind of scale we are going to see in the days to come. Before I come to the electrolyzer, I want to give a glimpse of what is the hydrogen market looking like and why it is there. It's simple. The world energy, if you see, is 20% electricity and 80% non-electricity. And whole efforts which has gone in the last 15-20 years is more to see that how electricity segment is cleaned and made green. And that's why we have seen a lot of solar and wind, right? That was the history what we have seen. But there is a limitation to which something can be electrified, the energy can be electrified. You still need coal, you still need petroleum, you still need nuclear, and so on and so forth, and which are all carbon emitting fuels. So how to clean it up? And that's why probably few years back, some of our friends across the globe has brought up this interesting concept of hydrogen. If it is produced through renewable energy, it can be called as green hydrogen. So that's the equation. So you can imagine that 20% electricity is still not solarized. It is still at a very, very minor size. And you need to make the 100% of the energy of the world clean, and hydrogen has a very big opportunity in front of us. Coming to applications, there are existing applications where hydrogen is being used. That itself will give almost like 80 million tons of hydrogen production, which is happening, that can be converted into green. Beyond that, there are new applications, like major one is the vehicles, like you are seeing EVs, you are going to see a lot of hydrogen vehicles. That's a new application. Followed by steel industry, which has been running on coal and natural gas, but we will start seeing the hydrogen-based steel production. So those are the newest segments. So these are the way market is going to emerge. And everyone knows that unless it is financially viable, unless it is competitive to the existing technology, this market of hydrogen will not pick up. Green hydrogen will not pick up. So the mathematics we have seen sometimes during our previous presentation that $4 to $6 per kg is the green hydrogen costs today. And the magic figure, many people say, is $2 per kg. How to reach $2 per kg? So that's the gap which as an industry, we all have to fill. That how $4 to $6 can be bought to $2 per kg. And believe me, whatever I have seen analysis, it is very much possible in the matter of 3, 4, 5 years max. In the interim, there will be requirement of support from the government and industries to see that how we can continue this journey of hydrogen, green hydrogen, and take it to a level where it can be inflection point, and then there is no looking back. Coming to the presentation now. Now, because of all this background, what is going to happen is that a lot of electrolyzers are required globally. Today, if you see, only 3 gigawatts of electrolyzer capacity is there. Maybe it has slightly increased now. Many electrolyzer people have already started their factories, but more or less it is 3, 5, maximum 10 gigawatt. But then you see where it has to go. By 2030, it is over 1000 gigawatts. You can imagine 100x jump. Or by 2050, even in a normal scenario, it has to be 9000 gigawatts. So you can imagine from 3 gigawatts to 1000 gigawatts to 9000 gigawatt, and in very beautiful scenario, it can be as good as 19,000 gigawatts. That's the volume of electrolyzer which world will be requiring to clean up as much as possible the unclean way of using the fuel. So if that is the case, where are these electrolyzer being manufactured? If you see, it is more or less concentrated around Europe traditionally. Now China has come up. Many electrolyzer companies are budding in China, but traditionally it was all in Europe. And in India, we are just starting. I will talk about the India very soon, but this is how it looks like. And some of the traditional way of manufacturing electrolyzers are changing. Now, most of the people are talking about modular electrolyzers so that it can be easy to manufacture, easy to install, and easy to operate. Almost like 17 companies has participated in the government of India scheme, what they call a site scheme. In the site scheme, out of 17, around 6 has been awarded. One of them is Ohmium, and rest of them are also now planning to set up the shop in India. One thing which is very important here, in solar industry in the last 10 years, what we have seen is that India has really missed the bus of Make in India for solar modules or any other solar components, to be frank. So this is something which we should not allow it to happen in the green hydrogen industry. And I think government of India has done a good job in setting up a right green hydrogen mission, as well as bringing up immediately the budgets, and also started to float tenders and awarding it for manufacturers as well as developers both. So in a way, we are good at that point of view. So this is the picture of our factory in Bangalore. It's a 2000 megawatt factory. Today, we can produce 2000 megawatt per annum in this factory already. This is all efforts of our leadership. Mr. Arnie Ballantyne, our CEO, has almost like 150 patents in the field of electrolyzers, followed by our CTO, Mr. Chok. He holds another 50 patents across the globe on the electrolyzer field. So these two guys put together efforts from 2020 onwards. And in the last 4 years, what we can see is that we have developed the complete R&D system in India. We have a manufacturing facility in India, and we have started to supply the electrolyzer across the globe. So this is what we have done in the last 4 years. Not only that, the complete supply chain, almost 80% of it is today indigenized. That means in supply chain partners who are supplying components to us to make this electrolyzer in India. So it is truly a Make in India product. Though our IP is American, though our headquarters is America, but more or less we are doing most of the work in India. So unlike many other players who has bid in site scheme or planning to set up shop in India, we have gone with PEM technology. So now the debate is not about which is good or which is bad. It is about what choice we made. We made a choice of PEM because we believe that if the electrolyzer has to run on solar and wind energy, which is very fluctuating, the best technology which can take that kind of fluctuation is only PEM. Alkaline will need a lot of external aids, which will lead to cost and efficiency loss. And so we have stick to our strength of PEM. Now, this is also important that some of the debate I had with Pawan in the afternoon about efficiency. We strongly believe that PEM has a good opportunity to bring down the efficiencies to the level which Reni has shared in his previous presentation, come closer to the technical and theoretical best efficiency. These are the reason why we choose PEM. Nevertheless, the application will not change. There will be applications where alkaline will be good. There will be application where PEM will be good. There are applications where SOTC will be very good. But we believe that majority of the application will need and can be served with PEM. We also have tied up with some premium institutes across the country and some in the outside our country, and we do it for developing good technology in-house and also to nurture young talent so that they can come into the electrolyzer field and contribute to this growing industry. This is the view of our factory which is inside. So we have got today A, B, C, D, E, F, 5 factories building. So the factory A and B and C is a smaller one which we started in 2020. That was a 500 megawatt factory. And today with the addition of plant E and plant F, we are almost 2000 megawatts. The initial buildings have been now converted into exclusive test beds so that like in the previous speaker has talked about the micro stack testing, how you can test small stacks, then make it small, bigger and come to the commercial scale. So that is a very important activity in any electrolyzer development. So we have those initial old factories of A, B and C dedicated exclusively for testing. Another important point which I want to cover is the components of the PEM technology, which is bipolar plates, porous material, stack electrodes and membranes. These are all done in-house within Ohmium, and more or less it is indigenized to the extent of 90%. It's all happening all in India. We believe in modular concept. The picture what you are seeing is nothing but stacking the electrolyzer on the ground and then going vertical. That way your footprint can be much reduced. So you can have in a building like 100 megawatts of electrolyzer. So like that 5 buildings you repeat, you have 500 megawatts of hydrogen generation plant. That's the beauty of the modularity. Each of our module is 3.15 megawatt. And why we are doing it? So that it can be mass manufactured like a volume production unit rather than a batch production unit. So you can just churn out this continuous that when the market is there and when the global demand is there, it can be fed very fast. Second is it can be installed very fast because it is modular and no cranes or big equipments are needed. With a forklift, you can go and install it. And finally, when it comes to operation and maintenance, each of the unit can be replaced in 15 minutes time. Or even if one unit is down, it is probably less than 1% of the system, which means that your system availability can be very high. That's the reason why we are going for modular technology. Last slide, where we have deployed around 10 locations globally, we have deployed these machines now. And out of that, 2 are operating today, producing hydrogen. And 2 more are going to be commissioned in the month of May. One will be the Emirates Steel, which is on the bottom right in Middle East. This will get online next month. Next month means May, yeah. I will just touch upon finally the challenges which I believe is there for the electrolyzer manufacturers. There are 3 challenges. One, the offtake. Today, the whole market is looking for offtake, whether it is developer, EPCs or manufacturers. Everybody want offtake. The only way to solve that problem is governments to step in, because otherwise the second alternative is smaller segment customers with smaller volumes, and for survival you can continue to do that, but big volumes will come from the mandates of the government so that we can get big volumes into the market. And major challenge which I see is supply chain creation. OMIUM took 4 years to create the supply chain in India. I think most of the manufacturers who are now willing to do it will also have to go through that. So as many participants are there in the supply chain across the country, they should participate and see they support this industry to bring up electrolyzer made in India. And third and final thing is standard and testing. This has to be standardized by force, by the government and industry association, so that there is some sort of standardization, so that supply chain is streamlined, as well as the testing procedures are streamlined, so that the performance can be measured at par for all electrolyzers. So that's all from my end. Thank you so much.
Thank you very much. Some questions for you. Let us have some discussions. I think you have said PEM is the best technology we can utilize for because of the electrical fluctuations which is happening in the country. One of the major thing. Whether you have done any studies on that?
Yeah, we have done studies, extensive studies.
Sensitive
Because we
studies.
have in one of the factory picture, you can see we have solar on the roof.
Ah.
That solar we are using to produce hydrogen. So those fluctuation you can see very easily through those studies.
And one you have done electrolyzer. What are the water usage implications
So
of large scale hydrogen
Yeah.
product? How can we mitigate this potential?
See, water would be a challenge in days to come.
Yes.
We need pure water or drinking water kind of source. But like what we have done is we have tied up with a European partner who can, with whom we are developing a system which can take seawater and produce hydrogen. So that is kind of like Rennie also covered that point. So that would be required in the days to come.
Right. We'll open up the questions after Mr. Pavan Mahdi's session. May I call upon Sri Pavan Mahendiratha, who will be focused on materials used in electrolyzer assembly, their significance and challenges related to their optimization for efficient green hydrogen production. Mr. Pavan is a business leader with over 28 years of experience and held senior leadership roles in multinational and Indian companies, including GE, L&T, and HAL. He completed his graduation from IIT Mumbai in 1991 and followed up with post-graduation from IIC Bangalore. His industry experience has predominantly been in power sector in gas turbines, gas engines, biomass, supercritical thermal projects, and hydrogen. He has held several responsibilities in the area, including strategy, sales and marketing, engineering technology transfer, EPC projects, and manufacturing. He has held several key positions as CEO with P&L responsibilities. In his green hydrogen at Max, he is responsible for overall business operation, which include BIO and EPC project, manufacturing and R&D of green hydrogen production. Prior to this, he was with L&D in various key roles over 7 years, where till recently he was part of key management and head of electrolyzer business of L&D's newly formed hydrogen business. In this role, he spearheaded strategy planning and finalizing collaboration technology for setting up L&D's gigawatt scale electrolyzer manufacturing business. Earlier, he had held several key roles in CEO of L&D's JV with Howden and head of strategy planning for L&D Power. May I welcome Sri Pavan Mahendiratha. Give him a big hand.
Thank you, Dr. Venugopal, for that good introduction. And first of all, I would like to thank Dr. Venugopal and the entire team here for for inviting me and Thermax to be part of this very, very prestigious and well-organized second green hydrogen conference. So thank you very much for that.
Seeing now is Alok Sharma's presentation. You have submitted. No? You have given.
I in fact checked with gentleman in the afternoon. Verify.
Naveen. You start.
Okay, so let me start off. Presentation is gets loaded up. So, I actually wanted to start with a little background of why Thermax started this green hydrogen business. Thermax was conventionally known as has been known as the boiler company. I'm sure all of you recognize and think many people think Thermax is a boiler company. It's been so famous for its boilers. But then Thermax has actually been doing many in renewable energy, in green hydrogen, which has not been noticed so much in the public forums and those kind of things. Thermax started, is one of the two companies in India who have got the technology for gasification of coal, and converting into methanol. Now Thermax has started a business of renewable energy where it is setting up its own renewable energy projects on build own operate basis. And biogas, Thermax has always been into the biogas industry. It has started into the CBG in many areas, wastewater treatments. And now, of course, Thermax has got a logo which says that it intends to be a trusted partner in energy transition. So in the last few years, Thermax has started going into the portfolio of, the green and the renewable energy in a very focused way. And as a result of this, there's this transition into green hydrogen also happened. And that is where about a year back, I think Thermax has been a late starter, but about a year back, this whole journey of the green hydrogen started. And if you can go to the next slide, please, I'll take you through. So if you look at the various segments, the manufacturing, Thermax today has 14 manufacturing factories, facilities, out of which 11 are in India and 3 are, outside India. 2 are in, one is in Europe and 2 are in the Southeast Asia. So it was very natural that Thermax also undertakes the manufacturing of electrolyzers. And that is where we have taken as one of the initiatives that we'll get into a manufacturing and localization and set up a gigafactory in India on the electrolyzer manufacturing. So that's the direction in which we are headed. We are looking at various technologies for which kind of, technology to get into. We could get into multiple technologies also. So this is one area we are actively looking into. We are looking to get into. The second important area is the build own operate. See, Thermax started into a BOO of many projects, including for let's say solutions where Thermax is actually converting biomass into steam and selling the steam to customers on a per kg basis, and it owns those plants. So we have a division within Thermax who does these kind of projects. It kind of sells steams and utilities and power to customers based on biomass. By the way, Thermax is I don't know how many of you know, but Thermax is the largest integrator of biomass in the country. So we procure the largest biomass as an organization, and we have many projects that we do on that basis. So this setting up of BO projects on green hydrogen is the second activity that we are looking to get into it. The third area where we are actively looking to get into is EPC. So, I mean, I did not tell you, but Thermax has probably done about more than 150 projects on a EPC basis, many of which have been outside India, and the majority has been in India. And this is for oil and gas, fertilizers, chemicals, pharma, food, steel, all those sectors, you know. So this is one area where we are very strong. Thermax is very strong, and we are very strongly looking to get into EPC of projects. We have already started participating in EPC projects for green hydrogen, and we have also built a team specifically for the EPC portfolio for green hydrogen. Also, if you look at the portfolio of Thermax, you know, there are many waste, you know, we do a lot of conversion of waste. It could be either to energy or to value added products. For example, there are so many waste heat boilers that we supply all across steel mills and all across refineries, fertilizers, etc. So the heat recovery is a very, very strong area for Thermax. We have chillers, you know, we are probably we are the second best chiller manufacturers in the world who are manufacturing the vapor absorption machines. And another area we want to look at, you know, if you look at, for example, an alkaline electrolyzer, 30% of the energy of an electrolyzer goes waste. You know, the efficiency is only about 60% or 65% of an alkaline electrolyzer. 25 to 30% goes as heat. So another area where we are looking at is how to kind of capture that waste energy which goes out of electrolyzers and increase the efficiency probably from 53, 54 units, which we talked about, to probably something like 45 or 40, 42 or 45 kind of, you know, figure, which I think Rennie also spoke of. So waste heat recovery is a very important part of optimizing. So we believe at Thermax, we have that strength, we have that, you know, DNA in our system, capability to look at waste heat recovery within electrolyzers, within the green hydrogen ecosystem, and try to, you know, get that delta improvement, which will make the cost of production of green hydrogen much lower. Finally, R&D. I mean, R&D is something very close to our heart. I think Thermax is one of the few companies which invests a lot on its own R&D. There is a program we have with NCL today to develop a AEM electrolyzer, which is going well. We have another program which we are running with Agarkar Research Institute in Pune and KPIT to have the biomass to convert biomass to hydrogen using anaerobic digestion. We have a pilot plant which is running in our factory in Pune in Chinchwad, and we are looking to scale that up because, you know, we believe that for a country like India, the biomass is so abundantly available that it should be used. Look at places where there is rural areas where there is less access to electricity but abundant biomass available. You know, you could set up biomass based hydrogen fueling stations, for example, which would be more cost effective to and also, you know, help increase the reach of transportation to these far flung areas at a much economical rate. We believe that with a good technology, actually, we can produce hydrogen at around less than about $3 per kg with biomass, is our belief in India. So these are the areas that, you know, led us to take a very strong foray in green hydrogen, and I think you will hear lot about us in the near future as we announce more and more projects, more and more concrete steps towards these various areas which I have talked about. That's the one part I wanted to speak about. Next, please.
Thank you, Bhavan. It is over.
I have some more.
Please, kindly finish it off.
So what I did was, in addition to this part about Thermax, I just wanted to talk about a few technological challenges which I believe are very important and needs to be taken, needs to be recognized very well. So if you can go to the next slide, please. Yeah, next slide, please. So one important challenge that we face in green hydrogen is the definition of green hydrogen itself. I'm sure all of you would have heard blue, green, purple, black, gray, all these kind of colors. Now what's happening is that one step has been taken from that, and what the various countries are doing is that they're defining what green hydrogen actually, what is green hydrogen, what is the definition of green hydrogen, or the green hydrogen standard, so to say. But what is happening is that different countries are having different definitions of green hydrogen. For example, India has come out, the MNRE has come out with a definition of green hydrogen, so that the CO2 of less than 2 kgs of CO2 should be produced per kg of hydrogen. Similarly, UK and Canada have 4 kg, and some of the other countries have different. And also the definition is also different, the scope. For example, if you look at Europe also includes the transportation of hydrogen as part of the definition. So this will be a big barrier in terms of an international trade, is what we think, because different. I think there is a big need to standardize this whole definition across various countries and have a standard definition. This is a one big challenge that I think will happen at an international stage. Next, please. Can you go to next? Okay. See, I've just brought in a case study where the world's largest electrolyzer installation in China at Sinopec, which is almost a 260 megawatts of installation, and where there are electrolyzers with 3 different companies, all Chinese companies, face the issue of not being able to go below 50% of turn down, and they were experiencing problems. And this problem has been publicized worldwide. And of course, this is one of the big challenges as we look into operationalization of electrolyzer. I'm not saying that this will be true in every alkaline electrolyzer, but these are the kind of challenges which will come up as we go into more and more installations even in India. So for example, if you look at this particular problem, alkaline electrolyzers typically have separators, which just allows both the H plus and the OH minus ions to go across the separator. And that's what has been conventionally used. But now, given this background, and people have realized that they need to go to membranes. For example, if you look at the graph in the bottom part, it will show you that the performance of the old ACFA separators versus the new membranes which they have introduced is significantly better and different. So this is one issue which has been faced recently. And also, some of the way people are looking to overcome this problem is by having a lot of buffer. So what that means is that there is a gas which is, even at part load, there's still a large buffer of gas which is there around the electrolyzer, so that the electrolyzer does not realize it's a part load, that kind of a situation, and still there is a buffer zone. So there are a lot of technical ways by which people are looking to overcome, but this is a problem which needs to be very carefully seen. Shaji spoke of PEM electrolyzers. One of the biggest issues of, I am a great admirer of PEM electrolyzer, by the way, in terms of their fast reaction time and their ability to adapt very fast to the varying renewable loads. But one of the very big challenges we have in electrolyzers, PEM electrolyzers, is the usage of iridium, which is in short supply. Typically, about 400 kgs of iridium is used today for every gigawatt of production. And if we look at the production which is planned, in the next 6 years, about 30 to 40 tons of iridium would be required, which is not available in the world today to cater to the current needs of. So this is a big problem of the PEM electrolyzers. So if you look at it, the second problem is a PPFAS membrane, which is not a very environment friendly kind of a membrane. And so for both these issues, there are many people are working on it. For example, H2E Technologies is a company which has developed a different kind of catalyst. Spark Nano is using a different kind of manufacturing process by which the iridium usage would go down by 80%. And of course, the US policy has mandated a clear requirement of an iridium recycling. And of course, for the PFS, now we have a different kind of PFS-free membrane, which is a PEEK membrane. So I think various solutions are happening, but for me, for PEM, this is one of the biggest issues which needs to be sorted out. I'll go a bit fast because of the time limitation. AEM is another emerging technology, but the problem about AEM is the short, very small stack size, which comes basically because the membranes which are used in AEM have to be used in a highly acidic kind of an environment, and they have very low ionic conductivity, which leads to higher cell resistance and a low H2 output. So for that, now we have the industry is coming up with composite AEM membranes. We are also working on that with NCL in the R&D project that we talked about. That's a very key part of our R&D project. And on the right hand side, you can see those new kind of membranes which are now getting developed across the world. And all of these are composite materials which have. So there are good developments in that front, and I think AEM will become an important technology as we go along. Solid oxide, I think Siddharth spoke about that. It's a very complex technology, but it's a very promising technology. Today, we are having a lot of issues in terms of degradation, in terms of the material decomposition, etc. The solutions are people are moving to advanced ceramics, and there's a company called Ceres which has come out with advanced metal supported design. So that kind of gives a very high durability. But I think solid oxide is a very, very promising technology, and we will see a lot of work. The cost of solid oxide will come down dramatically as we go in the near future. It might, as Siddharth also said, it might be very close to the alkaline and the PEM in the, let's say, 3 or 4 years from now. Lack of time, I'll not go through this in detail, but I'll just touch upon this. There are many other challenges in terms of the procurement of RE power, which the government has announced many steps, but I think many more steps needs to be announced. One simple example is that if you set up a, let's say 100 megawatt electrolyzer, you need a 200 megawatt of renewable energy power. But then if you look at the current rules, you can have a maximum connectivity of 1.4 times. So you can't set up a 200, you can't even legally set up a 200 megawatt RE connected to a 100 megawatt electrolyzer. So these are some of the issues, plus the banking. There is less clarity on the banking rules. If you do an ISTS, for example, taking a power from one state to the other, there is no clarity on how will banking work. So many issues like that need to be resorted. Waste heat recovery, I mean, if you go to solid oxide, you need to use a lot of waste heat. Will that be considered as a renewables source or not? That's another issue which needs to be looked into and clarified. Lot of demand charges are there today in usage of renewable electricity. We talked about the price of hydrogen. Today we are at about $4.5. I think we can, I see a pathway to reach about $2. And the pathway is that the capex has to come down by about 70%, and the cost of renewable energy has to come by about 35% or so. I think it's possible by the way things are going, and we should be able to reach that.
Okay,
So,
Pawan, thank you
so
very much.
I'm sorry of exceeding the
Yeah,
time, but
yeah.
thank you.
So, Pawan, we would like to hear from the audience. The discussion is open floor for the questions from the audience. If anybody is having any questions to any of the panel members, please, please give to the turban. Yes. Yeah.
Hello. Myself Amardeep Singh from Mahat Safex LLP. My question is regarding using of water for production of hydrogen. As since morning, I have been seeing that most of the people are discussing regarding using water for H2.
Yeah.
What about the wastewater?
Yes.
Because
Rennie,
just 1 minute, sir, just 1 minute, sir. Because as per some environmentalists, they say that Middle East countries were using hard water for their soft water requirement and decanting that water into sea, which has caused tremendous environmental changes, especially on Indian sea face. So what do you have to say about this thing, sir?
Okay, Rennie.
So I would like to address this question in two ways. The technology is also getting developed for direct use of seawater. So this is one area that people are working on for direct use of seawater. Second is that you can have different processes like your desalination is one route, but it is not cost effective as such. When you're doing this conversion, it is actually, you are investing a lot in that. Similarly for wastewater utilization also, it is all about the cost. Actually, it is adding up to the cost, but it is not, we cannot dispense it out because this is a problem going to come in the future. So it has to be seen in totality. So definitely this work has to happen. A lot of work has to happen in this particular area. That's what I would say.
Another question, please. Any other questions? Yes, please give the microphones very fast. 2-3 questions.
Up to what extent green hydrogen can be blended with NG, and what are the challenges for the green hydrogen blending?
You can answer.
Yeah, traditionally, with the existing burner system, we can blend up to about 15%. There is a traditionally, we have done prove out, and we have worked also in our furnaces and all those things. But as I think in the one of the session, I think was told that burner are also getting developed for higher blending. So we can accordingly develop the burner. But otherwise, traditional burner, if without changing the burner, we can blend up to at least 15% what we have seen without any problem.
Major thing is that PESO has given approval up to 7% of blending as of date. And we are expecting that if the effects of the blending doesn't have much problem in the pipelines, we will be going up to 20%. That's what the recent research, and in Germany and other countries, they are gone up to 20%. So we are expecting in the coming days, it will be possible. Yes. Next question.
Yeah, my name is Manish Khandelwal. I have a question for Shaji. Shaji, you said that the unit that you set up has a capacity of 2000 megawatt per year, right? So may I ask you, like, what is the lead time for, let's say, 200 megawatt stack?
So lead time based on the supply chain partners, lead time, etc. For a 200 megawatt, you can get delivered in 18 months.
18 months. Okay. And one more question, if you allow. When you said it can operate at high pressures, what is in your experience high pressure, or by the design, how much it can take?
So our machines are designed for currently 27 bar,
Okay.
and it will go up to 34 bar in the next generation by 2025.
Okay. Thank you so much.
Yes, please.
Good afternoon, sir. Myself, Hari Krishna. Sir, what is the life expectancy of membrane which we are using right now in the electrolyzer? And year on year, that efficiency also will come down. So how much efficiency will come down year on year, and what is the life expectancy of total
Can you
electrolyzers?
answer?
See, depends on the, for example, if you're talking of alkaline, most of these membranes have a life of almost about 60,000 hours today. Of course, you will have to do the proper O&M maintenance procedures and all that, but alkaline have about 60,000. PEM electrolyzers have slightly less, about 40,000. And of course, solid oxide doesn't have membranes, but PEM is about 40 and alkaline 60.
One more question, only one question we'll take up.
Good evening, sir.
Yes, please.
Myself Pranay Mohanty. I actually asked to Dr. Rennie that electrolysis is a very complex process. So if you are talking about water electrolysis, it is hydrogen as well as oxygen present in that process. So we know if oxygen present in hydrogen process, it will be a explosive mixture. So how could we taken care of this in this electrolysis process?
No, basically the separation occurs inside the cells actually. So suppose if there is any crossover happens, there is certain amount of crossover happens even through the separators actually. But that actually there are safeguards which is there inside installed along with the electrolyzer systems that it can detect what is the hydrogen crossover happening in the oxygen side and what is the oxygen crossover happening to the hydrogen side. So there are safeguards which are installed in electrolyzer systems that will detect what is the crossover happening and it will automatically shut down the system. So these are very important actually.
Thank you, ladies and gentlemen. Hope this session attendees got comprehensive insights into the challenges of green hydrogen production and the innovative solutions being developed by industry experts. All of them are BPCL, OMIUM, L&T, and Thermax. All of them gave a very good presentations and the significance of addressing challenges in green hydrogen production, importance of accelerating efforts to meet energy transition, emphasizing the technological innovation, market integrations, and highlighting the environmental and social impact of green hydrogen. This is a very important thing which we discussed today. Overall, the session provided a comprehensive overview of the challenges in green hydrogen production, showcased the innovative solutions, and emphasized the collaborative efforts needed to overcome these challenges for a sustainable and green energy culture and a future also. Thank you, ladies and gentlemen. Give these panel members a big hand. This is a great opportunity to thank them wholeheartedly.
Yes, it was indeed a very interesting technical session. Thank you, panel chairman and distinguished speaker. As a token of appreciation and remembrance, I would request panel chair Dr. R. Venugopal to present memento to Sri Siris Antrolia, sir. Thank you, sir. I would request panel chair Dr. R. Venugopal to present memento to Dr. Rennie Andrew. Thank you, sir. I would request panel chair Dr. R. Venugopal to present memento to Sri Saji John. Thank you, sir. I would request panel chair Dr. R. Venugopal to present memento to Sri Pavan Mehendi Ratta. Thank you, Dr. R. Venugopal, for conducting and concluding technical session 1. We are grateful to you for your effective moderation of this session and chairing one more session untiringly in this afternoon. As a token of love and affection, I would request Sri N.M. Surana to present memento to Dr. R. Venugopal. Thank you, sir. Now we will have a short break of 15 minutes. 6:15, we have just finished 6:30. Okay. Yeah, so we'll have a quick short break for tea, and then Sri Bhavin Shah will take us forward for the next session. Thank you.
Hello. Requesting all the delegates to take a seat. We are about to start technical session 2. Requesting all the delegates to take your seats. We are about to start technical session 2. Good afternoon, everyone, and welcome back from a short refreshing break. We are now starting technical session 2, and the topic is challenges in green hydrogen storage. Now we are pleased to welcome Sri Ashish Bhushan, Director Process and Engineering OISD, as a session chair for second technical session. I would request Ms. Shreya Shah to welcome the guest with sapling. Thank you. Have a seat, sir. Sri Ashish Bhushan sir is a chemical engineer with postgraduate diploma in business management, in operations and finance. He has an extensive experience of around 27 years in oil and gas, spanning in 2 refineries of India's largest oil companies. He has worked in various departments of oil refinery like operations, process and projects. He has a rich experience in petrochemicals, in which in different spans he has worked in a aromatic complex as well as olefin complex of a largest petchem of a public sector undertaking. He has attended seminars and workshops at various licensors and technology providers across the world. He is a certified OHSM ISO 45001 2018 lead auditor and is currently playing an instrumental role in enhancing safety in oil and gas companies of India. As a director, process and engineering OISD, his portfolio as a head of department includes refineries, petrochemicals, gas processing plants, and crude tank farms under the Ministry of Petroleum and Natural Gas. Sir, the floor is yours for the second technical session. Thank you.
Thank you, Bhavin. Good evening to all the distinguished guests, speakers, and delegates. It's going to be a challenging thing for me to chair this session. Basically, there will be 3 challenges. One is to match the previous chair, Dr. Venugopal, who has been a very experienced person, a very knowledgeable person. The second challenge is the organizers have already given you the card for 7:30 musical program. So we need to curtail things till then. And of course, the attendance has already gone down. So I fear that further if we go deeper into the night, there will be only chairs to speak to. So that's the second challenge. And the third challenge is, of course, the topic that we are going to discuss. So starting of the session, I would like to welcome or call upon the stage the speakers of the session. Shri Nitin Jansari, Assistant VP, Process Engineering, Inox CVA. This is Pooja Shah, Senior Manager, Linde Engineering India Limited. Shri Shivam Gupta, Project Manager, RHQ IOCL Delhi. Shri Saket Tikku, President IIChE-BRC. Shri Santosh Radhakrishnan, Vice President, South Asia, VRV. Shri Somnath Sarkar, DGM HSE and in charge Fire, Opal. Then Shri Naveen Jain, Director Time Technoplast, Mumbai. I request the organizers to present a welcome sapling to all the presenters. So thank you, ladies. So since we don't have much of time, so we'll start off this session right away. And of course, there are speakers who'd like to catch flight in the evening. So this program was scheduled up to 5:30, and then we are starting off it at 5:30. So the first speaker that I would, or rather for a panel discussion, Shri Saket Tikku, he is President, All India Industrial Gases Manufacturing Association. Shri Saket is the President of IIChE-BRC. IIChE-BRC is a sole national body representing major industrial medicinal gas manufacturers in India and abroad. He has over 30 years of experience in the field of industrial and medical gases. He is the Director of Esteem Gases Private Limited based in Mumbai, India. The company is engaged into manufacturing and distribution of industrial gases, welding transformers, welding rectifiers, welding consumables, etc., having factories in and around Mumbai. He is holding the position of a member of Oxygen Committee, which has been formed by DPIIT, Ministry of Commerce and Industry. Then he has ensured uninterrupted supply of medical oxygen in the wake of COVID-19 pandemic. In his capacity as member of committee, he has advised the government and Prime Minister of office on important issues related to medical oxygen. He is a technical advisor to United Nations. He is advisor to UNDP and to UNICEF both. He gives his expert advice on medical oxygen generation and storage. He is appointed by NITI Aayog as member of committee constituted for modeling of requirements for manufacturing. So right away, what we'd like to do is let him speak what are the major challenges which are being faced in the storage front of hydrogen, what he feels and what is his idea, since he's into lots of associations and membership with the government. So he's having quite a wide view of what is the thing which is actually going on in the world. So I'd welcome sir to just speak his own views.
Good evening. Thank you very much, Ashiji. Good evening, everyone. I'm going to speak about the challenges, a bit the kind of challenges which our members of the association, which they experience. My fellow panelists are going to speak on they are going to make a presentation, speak on the various aspects of green hydrogen. I will try to speak something which might, you might connect with. And I will try to speak in English as well as in Hindi, so that the people who have difficulty in understanding whether it's English or Hindi, so that everybody understands. See, as far as challenges of, storing hydrogen is concerned, as per me, I have, divided them into three parts. One challenge could be the procurement. When we are talking about the storing of hydrogen in the country, storage abhi bhi ho raha hai in the gaseous form, which were filled in the cylinders and stored in the cylinders. Liquid is also there, but then the volume jo abhi bhi hai, it's in the gaseous form. So the challenge could be, when we compress, high volume of gas into a small cylinder, that means we have to fill. Abhi, I think PESO has given or is about to give permission for 350 bar pressure. But eventually, if we want to compress, more hydrogen in a small container, that means the bar PESO has to, kind of approve for around 750 bar. Now the challenge is one in storing. As far as the, the procurement is concerned, that is one part. Procurement of the raw material for producing these cylinders, whether these cylinders are MSK cylinders or composite cylinders. So अभी भी even for 150 bar cylinders का raw material जो है, जो tubes आते हैं, steel tubes, अभी भी ज़्यादातर चाइना से आते हैं. We manufacture them in India also, but mostly it comes from China. Maybe because हमारे यहाँ पे volume इतना बड़ा नहीं है कि it suits the Indian manufacturers to produce it at the large quantities of this tube. Now forget about the composite cylinder, whether it's the carbon fiber ho, yeah, whether we import it from China or we import it from US or Europe. Yes, cylinders now are being manufactured in India, but raw material to bahar se aa raha hai, and it's very expensive. So storing hydrogen going ahead, when we are talking about the green hydrogen and all, volume बढ़ेगा तो अच्छी बात है, but वो viability नहीं आती है कि for a small, see, whether it is the big guys, whether it's Adani, Prerak ji यहीं पे अपना Reliance, Prerak ji यहीं पे हैं, whether it is Adani, rich boys, the rich boys club can afford a lot of things. They might be producing a large, but ultimately end user के पास जब ये hydrogen जाता है तो वहाँ पे challenges काफी हैं. So one challenge, as I said, it becomes expensive procurement of the raw material for making these cylinders. फिर एक टेक्नोलॉजिकल डिसएडवांटेज भी है कि वेदर 750 बार के वेल्व्स हमारे इंडिया में बन रहे हैं कि नहीं बन रहे हैं, वो एक चैलेंज आ सकता है आपको. द थर्ड जो विच इज डूएबल बट विच इज वेरी इंपॉर्टेंट आर द रेगुलेटरी चैलेंजेस. रेगुलेटरी चैलेंजेस मीन द रेगुलेटरी कंप्लायंसेस विच आर रिक्वायर्ड टू स्टोर हाइड्रोजन सिलेंडर्स. मजे की बात ये है कि एज ए सेड ऑन अ लाइटर नोट, द रिच बॉयज क्लब when they manufacture hydrogen, उनको उतनी compliances नहीं करनी है जितनी अगर 5 हाइड्रोजन सिलेंडर आपको कहीं पे स्टोर करने हैं तो आपकी जान निकल जाएगी साहब उसको अप्रूवल लेते लेते. So officers are here. I'm not talking about them, but the thing is, for storing hydrogen, you need a license in Form F. उसके लिए आपको कलेक्टर साहब से NOC लेनी है. Based on that NOC, you will get the permission to store. और वो आसान है नहीं. The fact है हमारे यहाँ पे तो 90% लेते ही नहीं है लाइसेंस. तो कौन जाएगा, सब लेने मर जाएंगे. कलेक्टर साहब को तो समझता ही नहीं है. वो 5-10 सिलेंडर के लिए जान जाएगी. कलेक्टर साहब तो बोलते हैं कि भाई यू गो फर्स्ट टू तहसीलदार से ले लो, पुलिस से ले लो, बहुत चीजों से. So my request would be, Venugopal ji said is very dynamic. Not that because he's in front of me, but he likes to conduct all these, जो आज हम बैठे हुए हैं, ये it is इनका खुद का पैशन है जो हो रहा है. हर एक रीजन में नहीं हो रहा है ये सब. ये आज से नहीं, मैं इनको कोविड के दिनों से भी देख रहा हूँ. See, hydrogen comes under a category called flammable gases. ये नॉन टॉक्सिक है, नॉन फ्लेमेबल है, फ्लेमेबल एंड टॉक्सिक गैसेस अलग है. नो फ्लेमेबल गैसेस में 3 मेजर जो हम देखते हैं प्रोडक्ट्स है. एक डिसॉल्व्ड एथिलीन गैस है, एक आपका LPG है, और एक आपका हाइड्रोजन है. नो ऑल दीज फ्लेमेबल गैसेस विच ऑल दीज 3 गैसेस फॉर. अब मजे की ये बात है, जो LPG सिलेंडर है उसके लिए आपको NOC नहीं चाहिए फॉर स्टोरिंग, क्योंकि वो प्रधानमंत्री साहब के यहाँ से आया था. हर घर पे LPG चाहिए, तो बोले यार इसको तो हमको हिट बनाना है, इसको ये रिक्वायरमेंट हटा दो. या एक सरपंच से आप ले लो. अब फ्लेमेबल गैस, हम इतने सब लोग ग्रीन हाइड्रोजन, बड़ी बड़ी बातें हो रही है, अंग्रेजी में भी हो रही है. वो सरपंच से लेना है मेरे को. सरपंच मेरे को देगा, जिसपे चीफ कंट्रोलर मेरे को देगा. चीफ कंट्रोलर, जॉइंट चीफ साहब मेरे को देंगे परमिशन बेस्ड ऑन व्हाट सरपंच इज गिविंग मी. और फिर इस देश में प्रधानमंत्री साहब कह तो रहे हैं, अच्छी बात, आई एम हिज ओन फैन, बट वी नीड टू गेट रिड ऑफ ऑल दीज थिंग्स. इफ यू वांट हाइड्रोजन टू बी स्टोर्ड, कुछ हालात तो बनाओ कि जो छोटा ट्रेडर है, सी एज आई अगेन सेड, द बिग गाइज, फॉर मैन्युफैक्चरिंग यू डोंट नीड द सर्टिफिकेट फ्रॉम कलेक्टर. फॉर स्टोरिंग 5 cylinders you need a NOC from the collector. And we are talking about a lot of things. So the challenge is, and let me also tell you that we at IIChE-BRC, it's not that PESO does not want to do it. उनको बोला भी नहीं गया. There are so many rules, so many things. इनके पास इतनी चीजें आती हैं, और जब ये कहते हैं, we are also to be blamed. When they ask suggestions from the public, do we need any changes to be done in gas cylinder rules? तो हम उसको चुप बैठते हैं. IIChE-BRC sent around 3 letters in span of 20 days asking people, hey, listen, we need to amend these cylinder rules. Let's talk to the ministry and talk to the PESO, suggestion दीजिए. एक भी सजेशन 5 लोगों ने suggestion दी है पूरे हिंदुस्तान से. So we are equally to be blamed when we are talking about the storage of hydrogen. So one of the challenges is for doing ease of business. अगर LPG में NOC की कोई जरूरत नहीं है कलेक्टर साहब की, तो साहब फिर हाइड्रोजन में और DO की क्यों जरूरत है अपने को? तो उसको, because this is not a safety, we don't want safety to be compromised. This NOC from the district authority is an administrative thing. अगर एक प्रोडक्ट में जरूरत नहीं है तो दूसरे में क्यों? तो हाइड्रोजन का अभी एज वेणुगोपाल जी यहाँ है कि जो भी इस मीटिंग के पॉइंट्स हो, whether the same can be shared in the head office, कि जो फ्लेमेबल गैसेस में इक्वल प्लेइंग फील्ड दें. आपने तो जो जितनी भी हम कोशिश कर रहे हैं, बड़े लोग तो बना देंगे हाइड्रोजन, पर एंड यूजर तक पहुंचेगा कैसे अगर इफ वी आर नॉट एबल टू स्टोर देम? तो अब जिसको 10 सिलेंडर स्टोर करने, 20 सिलेंडर स्टोर कर रहे हैं, वो तो जाता ही नहीं है पैसों के पास. कहता मरना है साहब, शेर की गुफा में जाओ और अपना सर दो. तो उससे अच्छा ये है कि साहब अब दूर ही रहो. बट विच इज नॉट प्रॉपर. We have to have approvals, we need to take licenses, but at the same time, we also need to request the department कि साहब ये changes जरा करवाएं, and I'm sure they will look into it and they will give us, they will consider these things. अगर hydrogen, green hydrogen going forward, it is a in thing. आप देख रहे हैं ना, हर महीना कोई ना कोई मिनिस्ट्री को खुश करने कहीं हाइड्रोजन पे सेमिनार हो ही रहे हैं. कल भी है, आज भी है, दिल्ली में है, कहीं पे. तो इट इज बिकम वेरी फैशनेबल. But where PESO is themselves, instrumental in having these kind of conferences, तो हमारी ये request होगी कि सर इस पे जरा थोड़ा ध्यान दे, compliance से थोड़ा let's ease out. So these were my main was the regulatory thing, the challenge. Second was procuring the raw material for manufacturing these cylinders, whether composite हो ये, because it becomes very expensive. फॉर स्टोरिंग. कंपोजिट सिलेंडर खरीदना बड़ा महंगा हो जाता है. जब तक इनका वॉल्यूम नहीं बढ़ेगा फिर तब तक इट्स अ चैलेंज. और वॉल्यूम तब बढ़ेगा जब हम इसमें वंस more oxygen, hydrogen is being used in the industry. And third is the technological challenge, जहाँ पे हमें valves बनाने हैं जो 750 बार तक हम लेके जा सकते हैं. As far as my knowledge is there, I think up to 350 बार तक हम valve बना रहे हैं अभी. तो 750-700 बार तक शायद हम नहीं बना रहे हैं. So for me these are the challenges which we need to look into, starting with the regulatory challenges, and that is what I have to say. And I think the other panelists will speak more the technical part of the hydrogen. Thank you.
Thank you, Shri Saket Tikku. So he has talked about the challenges, and especially, of course, unless we have the volumes, developing things or keeping it cheap is difficult. So most of them are still coming from China. Then he has talked about the technology part. And the third one is जो इनके सबसे दिल के करीब लगा, जिसके बारे में सबसे लंबा बोले ये, और that basically represents the manufacturer associations dukh dard bhi. That is the regulatory part and the getting the licenses and the clearances. So of course, the government is pushing things, and I think that these things will be addressed in coming future. So thanks a lot to you, Shri Saket Tikku. So rather than moving to any other questions, I'd rather suggest that we'll go into other presentations, and then in the end we can open the house to the delegates to ask questions. And one more thing is, since we are short on time, I'd request the presenters to curtail their presentations to 10 minutes or so. Or rather, less than that will be better off. बाकी अंत वाले को सुनने वाले कुछ लोग होने चाहिए. So now we are going to Shri Nitin Jansari. I'd request him to come to the dais. Shri Nitin is a mechanical engineer by profession, with more than 25 years of diverse experience in cryogenic storage and distribution equipment manufacturing industry. Currently heading the Design and Engineering Department of Inox India Limited. His area of focus and interest is designing of cryogenic storage like static storage tanks, transportable trailers, LNG fuel tanks for shipping and on-road vehicles. He is also responsible to develop new products for cryogenic application with respect to market requirement and technological upgradation. He is also active participant in various committees of SMPV, BIS, MED for formulation, updation of the regulation in the field of cryogenics. Sir, it's your floor now.
Okay, thank you. Good afternoon, all. Dr. Venugopal sir, SO team, and distinguished dignitaries on the dais and off the dais. It's good to see the involvement of different industry and getting connected through these events, connecting green hydrogen 2020. My special thanks to Dr. Venugopal sir, CGS team, IICHE and IOCL for organizing this wonderful event and inviting us to share our thoughts. Today, I'm going to speak about the liquid hydrogen storage. Since I'm from IIChE, I'll speak about cryogenics and the liquid hydrogen. Since morning, we are hearing a lot of gaseous hydrogen storage and other applications and electrolyzers and so on. I'll speak about the liquid hydrogen storage. We all know that hydrogen is very flammable and can cause fire and explosion if it is not handled properly. So my presentation will be limited to safety and the standards involved in the designing of the storage tanker now. Next slide, please. Next slide, please. Yeah, so the content I'm going to cover here is why hydrogen and why now. A liquid hydrogen bulk storage tanks, a case study I'm going to present for NASA, regulation and standard, typical flow scheme. I'll try to keep it short and more technical than typical hydrogen vapor flow and LNG flow, challenges and product offerings by IIChE. Next, please. Yeah. So why hydrogen and why now? So from this slide, you can see this hydrogen is nothing new we are talking about now. It is been developed since 1800. So from technological perspective, around 1950, if you'll see this chart, everything that needs to be known, that was known about hydrogen was known and developed. Be it the production of hydrogen by electrolysis or converting hydrogen into electricity by using fuel cells. In fact, even pilot demonstration of hydrogen as a potential fuel were being used for buses, trucks, submarines, etc. And there were 10 successful translating flights flew between Germany to USA. So this is the typical history of the hydrogen. And hydrogen as a as a fuel was not successful due to availability of much cheaper fossil-based fuels. It was the first OPEC embargo in 1975 that brought back the focus of alternative fuels, including hydrogen. The hydrogen as a potential fuel gained further prominence after the Paris Climate Accord 2016 and India's Green Hydrogen Mission 2023. Next, please. Sorry. This one. Okay. Thank you. So, if I'll talk about liquid hydrogen, let me brief something about the liquid hydrogen properties. As we all know that the liquid hydrogen is minus 253 degrees Celsius boiling point. The density is very low at 70.96 kg per meter cube is the density. Flammability range in air and oxygen, it has been displayed here. So in air, if 4 to 75%, it is quite a wide range in air, which is really flammable there. And in the presence of oxygen, even it is becoming more wider. And that's how it is becoming very crucial to handle hydrogen. Flame temperature is like in air, it is 2045 degrees Celsius, and with the oxygen enriched atmosphere, it is 2660 degrees Celsius. And let me tell you, the ignition energy required, it is very, very, very low. Even if hydrogen gas is flowing, let me give you one of the example. If hydrogen gas is flowing and one of the particle which is getting energized by say more than 0.02 millijoule, that can also ignite the hydrogen. So that's how it is very crucial and very dangerous, I should say. It is not a dangerous, but it is flammable. For which designing of a pressure vessel or a cryogenic vessel for liquid hydrogen become very crucial, because we all know that hydrogen is colorless, odorless, and tasteless, and we cannot see it. Even flame is invisible. Lot of standards are being used to design the tank, even the manufacturing of the tank. So I have listed down certain design codes which are to be used or which can be used to design the pressure vessel for cryogenic liquid. Piping codes are there. They are specially designed for hydrogen application. Cleaning standards are there. Safety valve sizing, that is again a very crucial part which we have to consider for any design calculation for safety valve sizing. And other recommendatory standards are also there, like CGA 5.5, CGA G5, CGA S3, and so on. So there are various standards available to use with, so anyone can understand the criticality, and it has to be used while designing. Okay, let me show you here the liquid hydrogen PNID. How it will be different than other air gas tanks. I have just tried to list down few of the things which are really making liquid hydrogen tank different than our liquid nitrogen, oxygen, or liquefied natural gas tanks. So all the liquid lines are vacuum jacketed pipings. Valves are being used for liquid, that is vacuum jacketed valves. For all liquid line, standard flange are normally not being used. However, standards are not saying no, but the recommendation is always to use bayonet connections. All outlets to vent stack. So there is a standard available there, which is CGA G5.5, which helps us to design the vent stack. How to design the vent stack, that is again a very crucial part. Purge connection for all the sections. Like if you can see here, oh sorry. If there are two walls and there can be a gas air entrapment in between, and if the liquid hydrogen is to flow from that line, then that air can get liquefy or even can solidify and can choke the line. So it is very crucial while designing the pipeline of the liquid hydrogen, because at that lower temperature, if air entrapment is there, that can mess up everything. There are many other things. I'll not stretch it more. Okay, let me show you the difference of flow. The left side picture is in one of the bare tank. The hydrogen is flowing. You can see that if hydrogen is flowing, you will not be able to see ice below. Whereas the right side picture, if you'll see, the entire hose pipe is covered with ice. What does that mean? It means the moisture is not getting condensed, but before that, the air is getting liquefied. And that's how the, can you start the video, please? Below the slide, there is a video. So you can, like what, something is dripping. It is not a water, it is not a moisture, but it is a liquid air. It contains liquid nitrogen and liquid oxygen. So that is how whenever we are using such pipes, such bare pipes for liquid hydrogen transfer, we have to keep it in mind that we have to have drip tray, proper drip tray, or proper route to pass through that liquid nitrogen or liquid oxygen, or I should say liquid air. I was talking about the vent stack. Designing of vent stack again it is not an easy task like a normal air gas tank or LNG tank, because standards has given some of the acceptable practices and non-acceptable practices. The upper side is shown as acceptable practices, which is not allowing the flow of gaseous hydrogen, even cold hydrogen or liquid hydrogen, that will not allow to flow back or to flow downward, which can affect the tank material. If it is the outer vessel is made out of carbon steel, then it can be severely affected. And the support system are also to be designed that way. Okay, I'll make it short. The same way, like even if the vacuum jacketed valves are there, there has to be purge port. Again, because of the same reason, the air can or maybe air can get liquefy or solidify within the stem. I want to give you one of the case study of NASA. This was a polite insulated tank. This was about 340 KL tank, and because of launching, they came to know that vacuum has lost, but because of launching, they could not stop using it. And after the launching, they have emptied it, and they have found that the air was solidified there on the inner vessel. And once the room temperature is achieved, the liquid that solidified air was dripped on the outer vessel of the tank, and that outer vessel was get cracked. So this is a typical example of one of the case studies. Product offerings, I think my colleague Mr. Savir Julka will explain you better tomorrow. So I'll not take much of the time for now. He will cover it. These are the various experience we are carrying as a company in-house. We have supplied 40 KL liquid hydrogen frame tank for transportation of liquid hydrogen. We have also supplied 15 KL tank to ISRO. These are the recent supply to Korea. This is 238 KL liquid hydrogen tank which has been supplied to Korea. With 3.5 bar was the MAWB. And the last one is again one more supply. 4 tanks are of 311 KL supplied to South Korea. So these are the supplied tanks from Inox. Last slide is the NER values are specified in the code. So whenever designer has to design, he has to keep it in mind that he has to balance between the support system for the heat inlet and the boil off rate. So the boil off rates are being defined here in the code for polite insulation and for super insulation. So we have to, I mean, any designer has to take care of it. And thank you very much. I hope I have not taken much time. Thank you very
Thanks
much.
a lot. Thanks, Mr. Nitin. You can come back. We'll get the questions later on. Mr. Nitin talked about the journey of hydrogen starting from 1800 to 2000 and then subsequently. So he talked about the liquid hydrogen bulk storage tank properties and then the dangers, of course, the visual representation of it really gives a memorable thing that what are the real dangers involved in it. And of course, this case study is also one of the factors which helps in recapitulating what actually is there. And so he talked about the supplies and the boil off rates, which is a major challenge in storing the cryogenic hydrogen. So next, I would like to call upon Ms. Pooja Shah. She is Senior Manager, Linde Engineering Private Limited. Ms. Pooja has done Masters in Chemical Engineering from DCET in 2007. She has 18 years of experience in the field of process engineering and safety engineering for hydrogen and ammonia plants. She started her career as a process engineer with Topsoe in year 2007. She was mainly working with hydrogen and its YCO plants. She joined Linde in 2018 as a safety engineer. She is currently working as safety lead for blue, green, gray, hydrogen and ammonia plants. Up to you.
Yeah. Yeah. Thank you for this nice introduction. And I would like to thank the IICHE committee for inviting Linde to share their experience on cryogenic storages. So, and thank you, Nitin, for taking us through this nice presentation of the technology behind the cryogenic. So I don't have to spend much time there. But yeah, before I would go on the actual challenges for the liquid hydrogen storage, I would also like to emphasize that, we are talking about the green hub in India. So this cryogenic storage or storage of hydrogen is a very integral part of this green development in any of the country or across the globe. So I'll just take you through. Yeah, this is about Linde. We are pioneered in supplying engineering and gases services. Linde is supplying engineering services for hydrogen and sustainable hydrocarbons and also in air separation units. And Linde is also supplying a lot of gases, which is rare gases, nitrogen, liquid oxygen. So Linde is pioneered in supplying liquid hydrogen, liquid nitrogen, liquid oxygen. Yeah, so this is a small slide upon our business. We are also venturing into the green hydrogen now. Yeah, so as Mr. Saket Tikku has mentioned about the challenges of the compressed gas storage, I will not take much emphasis on that, and I'll move to the liquid hydrogen storage. Yeah, so Linde has been supplying liquid hydrogen storage tanks for many decades now, and we are ranging from 3 TPD of the storage tanks to across 30 TPD currently in the market. The recent one is actually supplied in Texas in 2021. It is commissioned, which is 30 TPD. So Linde has a very established technology in liquefaction of these gases and also a specialized tanks which are actually taking care of the challenges that are actually brought by Mr. Nitin during his presentation. So to highlight a few is the loss of hydrogen during evaporation, which we also call as the boil off. So boil off is one of the major challenges right now in cryogenic storage. Just to give you a little bit more idea about the liquid hydrogen storage, in order to liquefy any gas, it requires a lot of energy. So liquefaction process needs a lot of energy. So basically, in order to keep it more efficient, it is required that the boil off rates are minimized. So currently, what he has mentioned in this presentation also is that the boil off rates are usually in the range of 1 to 5% for these gases. So which are huge. When we talk about the energy losses, it is a huge loss. So the major challenge currently in the industry of liquid hydrogen storage or the cryogenic storage is the boil off rates. Then when we talk about the feasibility, when we come to an Indian market scenario or any other market scenario, the first thing that comes into anybody's mind is the cost. So what is the cost involved? So currently for liquid hydrogen or cryogenic storage, the cost incurred is actually a good amount of cost is incurred because you need a lot of energy into liquefaction. You need a lot of space in order to make those plants available. When we talk about the compressed hydrogen storage, you need a compressor and a storage tank. But when we talk about a liquefaction plant, and that too, when we are talking about the capacities of say 1 gigawatt or equivalent, it will require a huge space or a huge plot and huge investment to build those plants and to store that liquid hydrogen. The other is like as I said, the boil off is one of the major issues. So we have the design of the storage tank itself was one of the challenges so far. It is still coming as a challenge because of the boil off rates, but companies are, venturing into different new models of providing these insulations or different type of tank design, which is avoiding or which is minimizing these boil off rates. And as I said, insulation is the key. So for Linde design, these are special double wall tank designs, which are internally insulated. They are vacuum insulated perlite insulation, which reduces the boil off rates. And that provides, a lot of flexibility in terms of the storing of liquid hydrogen. So this is a small example of a Linde liquefier. In this case, we provide an integrated solution of a Linde liquefier. And these ranges, as I mentioned, this ranges from 3 TPD to 30, 50 TPD. The one thing that is very important to understand here is that for smaller capacities, the losses that are incurred in liquefaction or the cost that is incurred in the liquefaction is much higher. If we talk about the numbers, we talk about around 11 to 15 kilowatt hour per kg of hydrogen is the amount of energy we require to liquefy when we put a small plant. But as we go higher in the capacity, the energy rate reduces to say about 8 kilowatt hour per kg of hydrogen. So it is more beneficial or it is more energy efficient to go for higher capacities. For smaller capacities, the cost is still higher, coming higher on hydrogen storages. So these are a few examples. Since Linde is also into the liquid fueling or hydrogen fueling station, so very recently Linde has collaborated with Daimler for liquid hydrogen storage and fueling station, where Linde has provided a huge liquid hydrogen storage tank and a fueling station. And we have multiple, I would say, references for liquid hydrogen storages. Yeah, these are some of the example of the liquid hydrogen storage tanks and liquefiers that are provided by Linde. Yeah, and Linde has also provided a green hydrogen plant in Leuna, Germany, followed by the liquid hydrogen storage. Yeah, that's it from my side. Yeah, thank you so much.
Thank you very much, Pooja. And of course, it was a good job that you completed within time limits. Pooja talked about Linde and its business. And of course, Linde has been doing this hydrogen job since a long time. She re-emphasized on the boil-off rate, which is a major challenge in the liquid storage. And of course, the liquefaction does require a huge deal of energy. As far as I understand, it requires around about 40% of the energy which is stored in the hydrogen to liquefy it. Whereas in a compressed gas, it will be somewhere about 10%. So if you liquefy it, 40% of the energy is lost. And then again, you boil it off, you again lose that energy. So there's a huge cost involved in the liquefaction process. And of course, those are the challenges which are being faced by the industry. And of course, I hope in the new future, things will be resolved. So next, I'd like to call Shri Shivam Gupta. He is project manager, refineries headquarters of IOCL. Shri Shivam is an accomplished engineering graduate from Madan Mohan Malviya Institute, University of Technology, Gorakhpur, with a bachelor's degree in mechanical engineering conferred in 2015, with a strong foundation in engineering principles and a passion for innovation. Shivam has continually demonstrated his commitment to excellence throughout his academic and professional journey. He has published articles on design and analysis of roll cage for an ATV, currently serving as a project manager at refineries headquarters of IOCL. Shivam oversees the installation of hydrogen production, purification, compression, storage, and dispensing infrastructure. In his role, he combines his technical expertise with managerial acumen to drive successful project execution and contribute to the organization's strategic objectives. Over to you, Shivam.
Thank you, sir. Good evening, everybody. I would like to take this opportunity to show my gratitude to IICHE and PESO for inviting all of us to share our experiences and also share the experiences along across the various industries. And I would also like to show my gratitude to Indian Oil Corporation for providing us with the opportunity to experience by involving us young engineers to set up new facilities like the hydrogen refueling stations. So we will be discussing regarding the risk assessment and separation distances for involved in the hydrogen storage, hydrogen installations. So I'll be taking you through why hydrogen is required. A lot has been already talked about why hydrogen is required now I will take another few minutes of yours. Then we will discuss regarding the various verticals which required to be strengthened to achieve a shift from the fossil fuel to hydrogen economy. Then we will discuss regarding the hydrogen storage, why we need to address the challenges which are related to various forms of hydrogen storage. Then we will compare regarding the types of storage, be it the physical form, which is already talked about in detail by the other panel members regarding the liquid hydrogen as well as the gaseous hydrogen, and the chemical storage form. Then we will move to the risk in storage, how the risk assessment has to be done, and how the mitigation has to be done, carried out, so that the risk associated with these hydrogen installation is not a trade-off with the safety of the personals. So we know that the air pollution is a leading cause for the climate change. The greenhouse gases being emitted by the transportation industry itself is around 8% of the overall greenhouse gases emission. 99% of the world population is breathing bad air quality. The Indian government has already committed to, via the Panchamrit scheme, to achieve the net zero carbon emission. So why hydrogen is required? The benefit of hydrogen being the byproduct, be it particularly for the transportation industry, be it the internal combustion engine or the FCV, the byproduct being water vapor only. So there is effectively no byproduct, and also the renewable energy can be utilized to generate hydrogen. Now we will discuss regarding the various verticals and the associated challenges. I will just give a brief regarding this, because we are going to discuss regarding the risk assessment for the hydrogen storage particularly. So the verticals related to production of hydrogen and the challenges associated with it are the high cost as well as the high carbon emission. A lot has already been discussed by the earlier panel regarding the hydrogen production and the challenges associated to it. Then for the hydrogen storage and the transportation or the handling of hydrogen, there are there are high investment cost or initial cost required to be incurred by the agencies. The storage facilities needs to be established, and also the transport methods needs to be efficient as compared to the present transport methods of carrying by road, that is effectively by pipelines only. That in an earlier session already described by Venugopal sir, that the approval for the for transportation through pipeline is yet to be explored by PESO in India. Then as far as the usage of hydrogen is concerned, the efficient demand has to be generated for replacing the fossil fuel with hydrogen. And for that, we need effective initiatives from the government. Some grants needs to be provided, some waivers or debates has to be provided by government. Now, why hydrogen storage is a concern? What are the challenges associated to it? We already know that the energy density per unit mass for hydrogen is way more than almost 3 times of gasoline. Whereas if we compare the energy density per unit volume for hydrogen, it is extremely low, almost 1/4 of gasoline. As we can see from the graph depicted on the right side, the hydrogen is on the rightmost bottom corner, wherein though the gravimetric density is maximum, the volumetric density is very less. As far as the other fossil fuels are concerned, the volumetric energy density remains constant, but for generating high volumetric density in case of hydrogen, the pressure has to be increased. Now we are going to talk about the various forms of storage of hydrogen. I have classified it into 2 groups. One is the physical form, and the second is the chemical form. In physical form, it is already been explained by the panel members that there are two ways where how we can store hydrogen by liquefying the hydrogen and by compressing the hydrogen in the gaseous form itself. The advantage as compared to the chemical form of storage being in the chemical form of storage, various chemicals or catalysts are required, which are costly as compared to the physical form of storage. The extraction rate of hydrogen in case of chemical storage is very low as compared to the physical form of storage as of now, because the chemical form of storage is still under development and it is still needs some more deliberations. Then the cost of the cost of generation of the cost of catalyst and chemicals is also associated with the chemical form of storage. However, if we see the one particular issue with the hydrogen was the low volumetric density. If we compare the volumetric density for the physical form of storage with the chemical form of storage, we can very well address that this increases in the chemical form of storage as compared to the physical form of storage. Ultimately, it has to be the chemical form of storage has to prevail so that we can get quite a good amount of hydrogen stored in a smaller footprint so that it can be a viable option. But as of now, widely utilized form of storage is physical only. However, if we compare the risk to reward ratio for compression of physical form, in particular in physical form of storage for the gaseous storage, if we compare how we are going to increase the pressure and what will be the ultimate volumetric density of hydrogen available energy, that is going to be on the diminishing side. If we see for 350 bar, if we are going to compress the hydrogen, it is going to accommodate almost 24 grams per liter. Whereas if we double the pressure, the volumetric density falls down to 40 instead of just doubling it. So the risk to reward ratio is still less as far as the compression is concerned. Now, before talking regarding the risk associated with the hydrogen storage, let's compare the two form of storage, the physical form of storage of hydrogen, that is the compressed gaseous hydrogen and the liquid hydrogen. A lot has already been deliberated regarding the liquid hydrogen, so I will keep it short only. Compressed gaseous hydrogen is an established technology, whereas liquid hydrogen is an energy intensive involves an energy intensive liquefaction process, and it is also cost intensive. However, the gravimetric energy density generated by liquid hydrogen is much more as compared to the physical form of storage in case of gaseous hydrogen. We can see the type of cylinders which are getting utilized for compressed gaseous hydrogen and the liquid hydrogen, wherein the energy density being produced is in the range of 2% for the type 1 cylinder, that is the overall completely metallic cylinder, in the range of 5% for type 3 and type 4 cylinders, and 6% in the case of cryogenic tanks. We can witness that the specific tank size required for per kg storage of the hydrogen in case of type 1 cylinder is 44 to 26 liters, and type 3 also, type 4 also 44 to 26 liter per kg because of the pressure thing. But for the cryogenic tank, it is going to be 14 liter per kg only. Also, the specific tank weight comes down from 125 kg per kg of hydrogen storage in case of type 1 to 12.5 in type 3, type 4, and 11.5 in cryogenic tank. So regarding the risk of hydrogen storage, so first we need to address the various properties of hydrogen. I will keep it short only. It has a wide flammability range, already explained, 4% to 75%. It has a low ignition energy in the range of 0.02 millijoule. It has a small quenching distance, that is, the flame can travel in small spaces also. It has a high auto ignition temperature, it has a high flame speed, it is highly diffusive, it has low density, and it has negative Joule-Thomson coefficient. So the risk being explosivity due to low density, flammability, it is highly flammable due to high flammability range, low ignition energy required for the generating the ignition, the asphyxiation possibility because it can highly diffuse in the environment and displace oxygen, and hydrogen embrittlement that is already discussed regarding the material of construction for the cylinders. Now, these are the risks which are associated with the hydrogen storage. So what we need to do is assess the various risk factors which can govern or which can prevail in a particular installation, so that the mitigation measures can be finalized. So for assessing these risk assessment has to be done. It is a systematic process of evaluating potential risk, which involves identification, analysis, evaluation, and mitigation measures. Of course, we are going to talk about the mitigation measures in a later stage in this presentation. However, we can talk about the quantitative versus qualitative approach of risk assessment. If the installation is going to be process intensive, the qualitative risk assessment approach is always performed regarding the HAZOP, like the HAZOP study, the safety studies, the SIL checklist, and everything. If the process intensive things are not required, then quantitative risk assessment needs to be emphasized upon. That is already being considered in various codes and standards, which we are going to discuss now. So normally, two of the standards are variedly discussing regarding the quantitative risk analysis. That is ISO 19880 and NFPA 2. Both have salient differences that we are going to discuss. The purpose of QRA being explained in both the standards is almost same. That is, the evaluate the risk and for due to unintended release of hydrogen. However, the approach is different. In case of one ISO, it is risk-based, which is a theoretical process, as compared to NFPA 2, which is the risk-informed approach, wherein the various multiple experimental data has been utilized, which was performed by Sandia National Laboratories. The major differences set out in the approach for developing a consequential model and performing the risk assessment is the leak sizes, the difference in considering the risk criteria selection, that is also called as IRPA, individual risk per annum. The ignition probability in case of ISO, it is considered to be uniform. However, in case of NFPA 2, it is varied. It ranges from 0.04 to 0.16, depending upon the leak size and the immediate versus delayed ignition. The facility representation is also different in case of ISO 19880 and NFPA 2. ISO 19880 divides the complete installation facility into different modules, whereas NFPA 2 considers the complete facility as a whole. Also, this leak sizes, which is considered in ISO 19880, is varying. However, the maximum size is 3%, but still the varying sizes starts from 0.18% to 3%, whereas NFPA 2, being on the more conservative side, considers the leak size as 3%. Now, what are the... Yes, sir. Okay, sir. Okay, just I will take 2 more minutes, sir. So what are the form of risk mitigation which can be utilized based upon the risk assessment? That is technical barriers regarding selection of material and everything. Human barrier, like installing bollards or installing containing the access by installing the boundary walls. Protective and preventive measures like gas detectors and everything. Safety distances that we are going to discuss in the next slide, and the regulatory and statutory licensing requirements. Now, separation distance is one of the risk mitigation measures which can be utilized to mitigate the risk assessed within the risk assessment, wherein the separation distance needs to be judiciously taken into account by considering the occurrence event within the acceptance criteria. The acceptance criteria being the acceptable heat flux, which can be based upon either NFPA or some other standards like OSD utilizes loss prevention in process industry by JR. Yes. Thank you, sir.
Thank you, Shivam.
Yeah, thank you.
Thanks a lot. So Shivam has touched upon the hydrogen requirement, which is basically for the cleaner environment he has emphasized. And of course, he has emphasized on the high cost of production and storage. Energy density he talked about. And of course, he has talked about the new thing about the chemical storage methodology. And if that's going to have a smaller footprint. And of course, he talked about the risk assessment methodologies and then the impacts on the hydrogen part. So next, I'd like to call Shri Santosh Radhakrishnan, Vice President, South Asia, Sales and Marketing, VRV Chart Industries. Shri Santosh is a sales and business development leader with over 30 years of cross-functional experience in driving revenue growth, expanding market presence, and optimizing operations in the industrial gas and LNG sector. After spending 9 years in major multinational industrial gas companies, he has joined BRB Group in 2009. He is a dynamic leader. He understands the industry dynamics, market trends, and customer needs. Santosh is responsible for sales and marketing of Chart and VRB products in India. Over to you. It's working. It'll work. Yeah, no. Switch it on. Yeah, that's done.
Yeah, good evening to you all. Thanks for CGS 2024 to giving an opportunity to Chart Industry to present in this August gathering. I will touch upon what are the hydrogen solution which Chart is offering, and some emphasize on the storage of liquid hydrogen. About Chart Industries, we are an US-based company which is having manufacturing facilities in India, China, and also extensively in Europe and US. We do in complete range of equipment, starting from if you see for hydrogen, from liquefaction to liquid cylinder. So we have a liquefier inside. The main components like cold box and brace aluminum heat exchangers and expansion turbines are our own. And once you produce the liquid hydrogen, it is transferred to the storage tank using vacuum jacketed pipeline, which also be manufactured. And of course, storage tank, and down the line for transportation by different modes and means like trailers, ISO containers, and even rail car. We manufacture in various parts of the world. So we have a Chart Water in group which gives the DM water plant to electrolyzer. And so for starting of the electrolyzer itself, we are having a footprint. And even though we don't manufacture electrolyzer, we have a investment in McPhee, which is a Canadian company which make electrolyzer. And once the liquid hydrogen is made, then it is liquefied. And then there are two modes of storage. One is for gaseous hydrogen storage. We have a company by name of Howden, which we acquired in 2023. And Howden is world leaders in combustion, which is having extensive various types of compression, from screw compressor up to centrifugal compressor. We compress up to 700 bar right now, and the technology for 1000 bar is in the pipeline, is in the R&D stage. In hydrogen, we are right from production to the usage. I'll skip a couple of slides so like from application side, we have from hydrogen liquefaction, hydrogen storage, green fuel, then green steel production, green ammonia, and blue hydrogen refueling stations, hydrogen pipeline, and hydrogen filling station. I'll touch upon a couple of. So we are present in various organizations. So coming to main hydrogen solution, this is hydrogen. So the main hydrogen, this is the typical view of a hydrogen liquefier, right from cold box to the storage liquid and to the transportation, and both vertical and horizontal storage. We manufacture these product out the storage tanks for liquid hydrogen is produced out of India also. So this is the hydrogen liquefier. So we have and the main component of the liquefier are cold box, base rubidium heat exchanger, and turbo machinery, which all is under our roof. So we manufacture from 5 TPD up to 30 TPD, and we are also in the process for manufacturing up to 150 TPD. And this is under the our compressors are one of the main constraint. So with the acquisition of Howden, we will be shortly achieving the one single train of 150 TPD hydrogen liquefaction. See, hydrogen storage is nothing new. This hydrogen storage is in the chart we have already produced around 800 large hydrogen storage tank from India. We have already manufactured India's largest liquid hydrogen storage tank for ISRO. It is 120 cubic meter, which is right now in operation in Shah Sriharikota. It is used during launch. So right now we are in our facility in Chennai. We are manufacturing 215 KL liquid hydrogen tank for a US based aerospace industry. These are the various mode of transportation of liquid hydrogen. 40-foot ISO containers, liquid hydrogen semi-trailers. Typical semi-trailers in US which we are running is 56,000 liters, which is carry around 4 tons of hydrogen. That's a payload of hydrogen. And also rail cars is also available, which is predominantly in US and also both South America and North America. So these are the typical liquid hydrogen tank. We recently supplied this to South Korea also from our US facility. And this is ISO container, which is under development. I think later on this year, this liquid hydrogen containers will be in operation. So we also manufacture liquid to gas fueling station, liquid to liquid hydrogen fueling station. And these are the concept of underground fueling to reduce the footprint. We also have underground storage system. We developed the technology a couple of years back. And we have a complete integrated testing facility in our new Prague facility, and where all the new components like we test extensively, including the component and including the storage and the mobile equipment. We recently tested our hydrogen mobility fuel tank, which is 450 liters, and which is successfully done the trials, and the trials are still going on. Once the trials are completed, we would like to bring this to India also. We are in touch with a couple of Indian OEMs for transport purpose, which we can use this for as a trial and for validation purpose. So these are the fuel tanks, which is currently it is having 16 bar working pressure and 450 liters, which can carry up to 40 kgs of liquid hydrogen. This will, to some extent, reduce the dependency of high payload, which typically it is not achievable using a gaseous hydrogen system because of the higher mass of the gas cylinder. Thank you. If there is any questions, I will take this afterward.
Thank you, sir. It was a very informative session. You talked about the chart and VRV functioning, and in fact, your company has presence in all the front of hydrogen usage, like production, storage, and usage, and of course into hydrogen liquefier also. And you have talked about the various mode of transportations that you're into: trailers, ISO containers, and you're into developing integrated solution for the industry. So that's a good thing to hear that companies are already into this field and they are doing good things, and we are soon going to see hydrogen in our economy. Now I'd like to call Shri Somnath Sarkar, DGM HSE and in charge fire, OPAL. Shri Somnath is a chemical engineer from NIT Durgapur with more than 23 years of experience. He is spearheading HSE and fire department of OPAL. He has got experience in refinery and lube oil processing plant. He has pre-commissioned, commissioned and completed major turnarounds in the industry. And of course, he has been instrumental in implementation of PSM also. He's a trained bounty and LOPA analyst by Mrs. Shell Global, certified lead assessor of ISO 45001 and 50001, and also certified by BARC for radiation safety in industrial applications. Over to you, Somnath.
Thank you, Chair. All dignitaries on and off the dais, respected Dr. Venugopal and their PASO team, IIChE Baroda and organizing committee. We really express our sincere thanks to all of you for inviting OPAL in this forum and giving us opportunity to speak on a topic which seems to be very, very interesting. See, I'll understand the paucity of time and I'll not take much time, but I'll try to make this topic very interesting for you. And I'll talk on the basics of the hazards that the manufacturing industries are facing, basically for the high pressure storage of hydrogen. I'll briefly outline my organization. I belong to NGC Petro Additions Limited. It's a petrochemical complex spread across your 508 hectare. The mother plant is our cracker unit, where we produce the ethylene in a nameplate capacity of your 1100 KTPA. We have downstream polymer plants, integrated offsites. We have our utilities, captive power generation plant of having capacity of 200 megawatt. If I talk about the hydrogen, since we are in the petrochemical business, we are not in the green hydrogen production. But if you look at this topic, the storage and challenges of hydrogen, I think it is equally applicable for all type of hydrogens. Maybe it is green, gray, or blue. So in this respect, I'll discuss on the hydrogen storage and its difficulties that organizations are facing and how we are overcoming these difficulties in OPAL. For OPAL, this hydrogen storage we are having in our offsite facility. I'll just briefly talk about the hydrogen storage facility. It is a vertical bullet, fully fireproofed, having its integrated piping, compressor systems, and its diameter is around 4 meter, 21 meter height, 185 mm thickness. So you can understand the volume, and the pressure that we are storing the hydrogen is 132 bar. So also you can understand the hazards that we are having by storing this hydrogen in a very high pressure. The hydrogens, what we are producing during the pyrolysis process in the cracker unit, it is in the range of 1200 kg per hour. And whatever hydrogen that we are producing in the pyrolysis process, out of this around 96 kg per hour, it is consumed in the polymer plants. Our balance is taken as a fuel. Now, for the polymer plants, if we want to keep our business run, then what to do if there is any upset in the DFCU plant or in the cracker plant? In such case, we are having an isolated storage where we store the hydrogen, and that is in the capacity of 2920 kg, and that can supply the hydrogen for around 24 hours. But to make the redundancy or the operational flexibility, what we have done, we have also set up a very small facility of hydrogen generation, which we call as a hydrogen generation unit, or in brief HGU, where we do the reforming of the naphtha. We take the naphtha and we heat up the naphtha with the high pressure steam. We do the hydrotreating and the desulfurization of the naphtha. We take it to the reforming unit. We reform the naphtha. We get the hydrogen gas mixed with certain other impurities like CO, CO2 and methane. We take it to the shift converter to get the maximum yield out of it. Then we pass it through the PSA unit, and ultimately we get the 99.99% hydrogen, which is the purity requirement for our downstream plants. Now, if I talk about the hazards of the hydrogen and how to mitigate it. Now, for the industries, there are three basic hazards that hydrogen is posing. I am not talking about the other hazards of the hydrogen because my other speakers, they have already covered it. The three basic hazards for which it is posing the maximum challenges to industries like petrochemical, and where we are handling the hydrogen in a very extreme environment where the pressure and temperature is very high. First is the negative Joule-Thomson effect. Second one is the hydrogen embrittlement. Third one is the HTHA, that is the high temperature hydrogen attack. Apart from this, the complexity of the facility siting, because we are storing the hydrogen in a petrochemical environment, where it is the neighboring facilities are also having the flammable chemicals. So protection of this facility is also very, very challenging for us. I'll briefly talk about all the challenges and how it is mitigated. If I talk about the negative Joule-Thomson effect, you know that negative Joule-Thomson effect, it happens with the gases which is having the inversion temperature which is more than its critical temperature. If I talk about the inversion temperature, it is the temperature during the adiabatic expansion of any gases, the temperature which is having the coolest effect. It is called the inversion temperature. But for all these gases, the inversion temperature is more than its critical temperature. It gives the negative Joule-Thomson effect. Negative JT effect, it means once the gas expands, the temperature increases. So if I store the hydrogen in a high pressure, and if I want to depressurize the bullet, if I want to transfer the hydrogen to some other process unit, so automatically the hydrogen pressure will get reduced. If the hydrogen pressure gets reduced, the temperature increases. For negative JT effect, the only solutions which is viable for industry, that is having a very good engineering control or the basic safety at the design itself. For our case, we are having interlock, we have inbuilt TT at the bullet top, which is having interlock with the ROV at the downstream, at the depressurization line. And if the temperature shoots up, automatically the ROV gets closed. Apart from this, during the transfer of this hydrogen to other units, we are also having the DCS control, we are alarm, where the panel officers activates the ROV closures apart from the interlocks. So what I mean to say, for negative JT effect for industries, those who are having this problem, the only solutions which is viable for industries, having a very good interlock in place, maybe in the level of SIL 2 or SIL 3. If I talk about the hydrogen embrittlement, so hydrogen embrittlement happens in a very corrosive atmosphere. Generally, it happens in the corrosive atmospheres. Suppose in the stream, suppose I am carrying the naphtha, as I have told you, we are reforming the naphtha. It can have the sulfur impurities. So basically, for the sulfide corrosions, it happens that during the exposure to the sulfide corrosions, when the metal surface is exposed to it, hydrogen atoms get converted to hydrogen ions. Hydrogen ions get diffused into the metal surfaces. And the sulfide, that also helps to uptake the hydrogen ions into the metal surfaces. If the hydrogen ions get intake into the this particular metal surfaces, what happens? It causes the cracks within these particular surfaces, or it reduces the ductility of that particular metal. So if this particular metal is it is put into stress, it may be thermal, it may be any physical stress, it develops the crack. So it is called the hydrogen embrittlement. So it is basically the corrosiveness that is actually converted into the hydrogen embrittlement. Hydrogen embrittlement is very, very dangerous, but the only thing, the hydrogen embrittlement happens in a very low temperature range or at a range up to the 150 degrees centigrade. So what happens if the hydrogen embrittlement happens? The only thing that we have to do, that we have to do the desulfurization as much as possible. So if I can reduce the corrosive environment from the my process stream, then obviously the hydrogen embrittlement will get reduced. Apart from this, the operational controls, your frequent M&I activities, that will also help the hydrogen embrittlement. Hydrogen embrittlement, these properties actually started from it was invented in 1875. And still today, the industries are still studying on various aspects of the hydrogen embrittlements, and they are taking their own course of actions, own control measures. But the basic thing is this, like us, we are doing the hydro-treating of the naphtha, we are doing the desulfurization of the naphtha stream, only to remove the hydrogen or the sulfides from it. Next, I want to talk about the IIChE effect, which is high temperature hydrogen attack. It is because of the Nansen curve that API has recommended in API RP 941, the Nansen curve, which is the curve depicts the relation between the operation temperature and the partial pressure of the hydrogen. High temperature hydrogen attack can happen in two aspects. Either the operation temperature is high or your hydrogen partial pressure is high, or both is high. In such case, the hydrogen high temperature hydrogen attack can happen. Now what happens in 2010, Tesoro refinery, they encountered a major accident where during the M&I activity, one of their heat exchanger failed catastrophically and 7 people died over there. And after that, it was found out the main cause of this incident was IIChE. And based on this, the Nansen curve was again revised, and it was suggested to reduce the temperature range to 204. Now, based on this, the industries are taking actions, and as per the recommendations, the metallurgical change is one of the best possible counter mechanism for IIChE. For OPAL also, we are doing the metallurgical change of entire pipeline, which is exposed to higher temperature. In such case, the molybdenum and chromium based alloys, these are very, very useful for this high temperature hydrogen attack. Apart from this, the operational control, the welding defects and operational upsets, these are also needs to be taken care to counter this high temperature hydrogen attack. Gentlemen, what I want to say over here, hydrogen and its hazards, it is a very challenging for us. It is not only the literature that we are having, the standards we are having, but also the industrial experience matter much. So let us have this opportunity with these discussions. We take forward this particular challenge in our places, and whatever the basic things that we are adopting in our practices, whatever the safety best practices that we are following in our industries, that we need to follow. And also we need to follow the guidance which has been given in the standards, various standards. With this, I really thank to all of you for listening us. Thank you.
So, thank you, Somnath. Somnath has talked about the activities that is being carried out in OPAL with respect to hydrogen. Of course, hydrogen is being utilized in refining and petrochemical industry from a long time. And he talked about the Joule-Thomson effect and the hydrogen embrittlement and IIChE attacks. And he has talked about the interlocks and the engineering specialties which are required to prevent it or make the system safe. Now I'd like to call Sri Naveen Jain. He's Director, Time Technoplast, Mumbai. Sri Naveen is an electrical engineer from IIT Delhi. He's a polymer processing expert to the go. He heads the dynamic R&D team who are responsible for new product and process development. Under his leadership, company had developed. Would you like to go? I said, probably you said that one. Okay. Sri Saket Tikku has got a flight to catch, and probably the airlines don't like to leave him behind. So just hand over a memento to him before he goes. So we hope there are no shows in the aircraft. They'll be in time. Right, over to Sri Naveen Jain. He heads the dynamic R&D team who are responsible for new product and process development. Under his leadership, company had developed Type 4 composite cylinders for storage and transportation of LNG and CNG gases for domestic and overseas market. His passion for developing new manufacturing solutions, improving and bettering this process. Time Technoplast is in the final stage of development of Type 4 composite cylinders for storage, transport, and onboard applications of hydrogen gas at high pressures. Over to you, sir.
Thank you, Chair, for the introduction. I thank you, organization, and Dr. Viru Gopal for inviting me for this presentation. Since morning, we are hearing about the hydrogen storage and challenges in hydrogen production, storage, and other things. Now, we have discussed a lot of things about the storage in liquid form, gaseous form, or other things. I have big presentation, but I'll skip a lot of things in that one because time is short. We'll directly go to the storage in gaseous form because we are manufacturing cylinders for the storage of the hydrogen in gaseous form. So I'll directly go to that. There are two major common forms of the storage of the hydrogen. One is the liquid form, another is the gas form. In liquid form, storage, regarding storage, our panel speakers have already spoken to it. In gaseous form, I'll talk about the gaseous form. So there are 4 different kind of cylinders which are used for storage of the hydrogen in gaseous form. Most popular and most common since ages cylinder which is available is the type 1 cylinders. Basically, cylinders are divided into 4 different types: type 1, type 2, type 3, and type 4, depending upon the construction of the cylinders. So type 1 cylinders are the all metal cylinders where everything is, these cylinders are made out of a tube. Both the ends are formed, and then necks are formed on the both the end, and walls are fitted in this one. These cylinders are very heavy, and embrittlement, what we are talking about, is also a question mark in this when we are storing the hydrogen. Another thing is maximum pressure what we can go in these cylinders is up to 1000 bar, but then weight becomes very, very high, and because we have to maintain the wall thickness, so it becomes uneconomical and very heavy for the transportation. Second generation cylinders which came into the market was the type 2 cylinders, wherein it was a similar form as type 1 cylinder, but wall thickness on the body was reduced and it was covered by the composite material to reduce the weight. Of course, here weight pressure carrying capacity was the same, and embrittlement problem was still remain the same. And they were slightly lighter than the type 1 cylinders, but still it was very heavy. Third generation cylinders came wherein it was all composite cylinders wherein fiber was winded from end to end, and they were using aluminum liner in this one. Now, aluminum liner, here weight reduction was almost 50%, and we can go up to 550 bar pressure again in this one. But with the aluminum liner, embrittlement problem was still continuing if it is not processed properly. So 4th generation cylinder which came is the type 4 cylinders, wherein liner is also the polymer liner, all polymer, which are 70% lighter than the type 1 cylinder, that is steel cylinder, and also can go up to 1200 bar working pressure. In this, This is the construction of type 4 cylinders. You can see there is a polymer liner inside, which is in yellow color. This polymer liner is made of special material by different technologies, so that hydrogen permeation is also controlled in this one. Then the yellow color, orange color, what you see is the carbon fiber, which is winded on top of it. And then we provide a protection layer on this. Then both the ends are protected by a polyurethane cover, so that when during transportation or handling, if any impact is coming on the corner, that is taken care of. Valves which are fitted in these walls, in these cylinders, are having the special walls which is having temperature indicator or temperature controller on the tip, which goes into the gas inside the cylinder. You know, when we fill the gas in the hydrogen in the cylinder, inside temperature increases. So these walls are a very special wall which are connected to the filling system. If temperature increases beyond certain limit, then it automatically reduces the flow rate of the filling. That way it is controlled. The benefit of these cylinders is they can work between minus 50 degrees centigrade to 170 degrees centigrade. We can go up to 1200 bar working pressure, and weight to liter ratio is very, very low. It is only 500 grams per liter of the water capacity. And it has very low maintenance cost since it is all polymer. So there is no question of the corrosion. Outside also we have carbon fiber and protection layer. So even in humid and corrosive atmosphere, these cylinders work very well. Second thing, they are very light in the weight. So when we are transporting the hydrogen, at the place of transporting only iron, we are transporting more gas in these cylinders. I'll give you one small example which we have for the CNG transportation. A truck load which can carry 405,000 liters of gas in a metal cylinder on the same footprint, same truck. If we use composite cylinders, we can transport 9,360 liter of the water capacity of CNG, which is almost 2.2 times higher than the metal cylinder. So we save a lot of money, like we have only one truck at the place of two truck, only one casket at the place of two caskets, and also save a lot of transportation cost that and by that carbon footprint we save. These are some of the application and pressure ranges, what is being used in the composite cylinder, like for gas transportation. World over 350 to 500 bar is the most common pressure range. For bus and truck application, it is 350 to 700 bar. Cars also, it is 350 to 700 bar. And for ground storage, it is 500 bar to 1000 bar. And people are still working on this. Research is going on to increase it further. In India, we are developing a cylinder which is working at working pressure of 350 bar, and maybe in future we will go for 500 bar. Just to give you an example, what is the weight and hydrogen carrying capacity of the cylinder? On the right side, you will see 100 liter water capacity composite cylinder for 350 bar working pressure will weight between 350 to 450 kgs only, which comes to about 350 grams per liter. And in when we see hydrogen filling capacity at 350 bar, 100 liter cylinder can carry 2.4 kg gas. 500 for same cylinder at 500 bar can carry 3.2 kg gas, and at 700 bar 4 kg gas. These are some of the examples of for the transportation of the gas by in the caskets. Like if we are 10 feet casket, these are the first figure which you see is the casket with the type 1 cylinders, metal cylinders. Second one and third one are the type 4 cylinders. So in 10 feet casket, 10 feet length of the casket, and 8 feet is the width of the truck. According to that, it is designed. Water volume comes about 8,000 liters, and we can carry at 350 bar 192 kg gas, 500 bar 258 kg gas, and 700 bars about 320 kg gas. Same way, if we go for 40 feet trailer, it can carry, it will be 37,800 liter capacity, and it can, at 350 bar, it can carry 807 kg, and 500 bar, 1160 kg, and 700 bar, 1512 kg. Now, main challenges which are coming in this one is carbon fiber is not available in India. We have to import it from outside world, and the carbon fiber which is used over here is same carbon fiber is being used in the defense industry also. So because of the war, there is a lot of fluctuation in the prices of the carbon fiber and availability of the carbon fiber. Second most big challenge comes in the supply of the valve. Because of the low volume, there are very few people who has developed this valve. Few in Europe, few in the US, and one company in Korea. But they are not ready to supply in India because volumes are very, very low. And price is also very, very high for the valves. Second thing, when they come to India, we have to take approval from the government. For low volume, nobody is ready to take the approval. So we have to take approval ourselves. So these are the main big challenges. This third thing is testing equipments. For these cylinders, testing equipments are very, very costly, because working at such a high pressure, testing equipments also become costly. These are some of the standard for the cylinders. Like for mobility, those cylinder is the same water volume, same working pressure. But for mobility, there is a different standard, different test. And for gas transportation, there are different volume, different standards and different tests. So we have to, for same cylinder, we have to go for 2 different tests. Now about Time Technoplast. Time Technoplast is a Bombay-based multinational company. We may have multiple products, and having a turnover of $550 million, having presence in 11 countries, and we employ about 5,000 employees, and we have more than 900 institutional customers and 45 manufacturing facilities across Asia and MENA region. We have our own R&D team of 50 people who work around the clock on this product. These are some of our customers. Now, these are the products which we have in composite segment. LPG cylinder from 5 liter water volume to 47 liter water volume. These are used for domestic LPG. Again, these are type 4 cylinders. Then we have cylinders for CNG mobility, wherein we make the complete cascade and give it to the supply to the CGD companies. Then we also have oxygen and type 3 cylinders in oxygen and breathing air. Here we have gone for type 3 cylinders because oxygen is not compatible with the polymer liners. Cylinder can explode during filling. Another one is air tank we have developed, which is used for the buses and trucks for the storage of air for braking and suspension system. Then we also supply this fuel tank. These are some of the testing facilities what we have, and the machines, robotic machines what we use for the manufacturing of the cylinders. Here, very important thing is repeatability of the program. Like you want one cylinder, then second, third, fourth, all have to be in the same fashion. So we went for this German machines which are robotic control. These are some of the tests which are performed on the cylinder. This I am showing you to give a confidence that how composite cylinders are very safe, being made of plastic. But there are so many stringent tests on this, they become more durable than a metal cylinder. Hydraulic proof pressure test, which is conducted at 1.5 times of the working pressure on each and every cylinder before it goes into it is supplied to the market. Hydraulic volumetric expansion test. Here also we test on each and every cylinder what is the expansion when we reach to the test pressure, that is 1.5 times of the working pressure. Now cylinder burst test. This test is conducted on the batch of 200 cylinders. Here burst test main criteria is cylinder has almost 2.6 times of the test of the working pressure. So a cylinder of 350 bar working pressure, minimum burst pressure requirement is about 1100 bar for that one. And our cylinders pass about 1250 bar for that one. Cycle test where out of a batch of 200 cylinders, we take one cylinder and conduct the ambient cycle test wherein we pressurize the cylinder to the test pressure, that is 1.5 times of the working pressure, and do the cycle, continuous cycles for depending upon the life of the cylinder, like 500, if it is, we are giving service life of 20 years, then 500 cycles per year, that means about 10,000 cycles it has to pass, then only we clear the batch. Then environment, just one minute. Then these are the other tests. Most important is this fire test. Sorry. Fire test wherein we put the cylinder in the fire, and the requirement is it should not blast in 5 minutes time of the fire. That time fire temperature of the fire is about 700 degrees centigrade, and this cylinder does not explode even then. And after that also cylinder punctures in the body, or it gas leaks from the body or from the safety valve, but it does not explode. Unlike metal cylinder, they explode at a certain pressure. These are some of our future products. We are developing this. We have already developed 150-liter cylinder with 350 bar working pressure for hydrogen application for mobility, and that is under testing. Other cylinders what will be working is 60 to 350-liter capacity with a working pressure of 350 bar to 500 bar working pressure. Then we will be developing these cascades 10 feet to 20 feet size with working pressure of 350 to 500 bar. Then we have already in the process of developing this type 4 composite cylinder for scuba diving and also for breathing air. And fourth one product which is under development is type 4 composite cylinder for fire extinguisher. This is a big problem in the market because current fire extinguisher, they get corroded very fast, and our industries are having corrosive environment. When they are installed within 5-6 months, sometimes they lose their properties, so we have to replace them immediately. So these are some of the products which are under development, and we are basically a composite company, and we are trying to develop all the product which can be cylinders which can be produced in composite and give the safe and better packaging in India. Thank you very much.
Thank you, Shijen. So it was quite an informative session. He has presented the types of cylinders which are probably being used, going to be used in the hydrogen storage. He talked about the special requirement of the valves particularly, and then the India is like catching up with the global standards of high pressure storage. And then of course he talked about the cascade storage, and his company is into the manufacturing of lots of vessels. And of course, I think that lots of you must have visited his stall, and you might have got a visual look at what is the real storage things that are coming up. So I think with this presentation ends up here. I think we are quite short on time. 7:30 is the time to start on in the session of the music. So I'd suggest that at the most 2 questions can be asked in the house. Anybody?
Thank you. My name is Nikhil. I have a question for Naveen. Are the manufacturing processes compliant with the relevant standards and regulations? For example, how you ensure the quality of the surface finish or the coating of this composite type 4 cylinders?
Everything is specified in the standard, and we follow the same process, same standard, because standards are designed, are specifying the testing requirement and performance requirement of the cylinders. So based on that, we decide and design everything for the cylinders.
Okay. So they are now very much the rules and regulations are including all these things in India.
Yeah. For cylinder standards, there are ISO standard, there are EN standard, which have been adopted by the BIS and the PESO. So we are following those standards for the cylinders.
Thank you.
My name is Maksud Sheikh. I'm from Ultra Gas. Question is to Pooja and not to Nitin. Pooja, you spoke about the BOG rate. Somehow it attracts me because it involves money. So in BOG, in order to bring down the rate reverse from 5% to 1%, if somebody is targeting, what is more important to look at? The insulation between the inner and the outer vessel, or aging of the commodity, or something else?
Actually, this is still under development. There are more things which are coming for the BOG. Currently, when we talk about 1 to 5%, 5 is going really on the high side. One, I would say more can be accommodated by the means of insulation. But there are other things also involved. When we talk about bigger storage tanks, then BOG rate of BOG reduction in rate of BOG can be done by multi-layer insulation as well. But at the same time, I would also say that we have to look into the possibility of recycling it back, which currently in this scenario is less cost effective because of the cryogenic technologies. You need much more
Our
energy.
experience is other way
Yeah.
around.
Okay.
The more we recycle, the more the BOG rate. And
Okay.
we can deliberate it in tomorrow when I'm going to address the challenges.
Okay.
So Nitin has been working with me on this. We are struggling. What has been the experience at the Daimler plant for the hydrogen? I am referring more from LNG perspective.
Okay.
But what has been the experience of that installation?
I
Any
will come.
idea?
I'll come back to you on this one maybe
Thank you.
tomorrow.
Thank you very much.
Yeah.
Yeah.
So thank you very much. It's really heartening that audience is still there. Of course, I had talked about 3 challenges in the initial stages when I started this session. One was meeting the predecessors level. Dr. Venugopal is quite a knowledgeable and a capable person. So I can't meet his level of chairing this session, of course. Second challenge was finishing in the time. So I thank my speakers, and you'll all appreciate that whosoever has given a representation for appraisal, they might be knowing that saying things in a small thing is very important, 200 words or so. So nowadays, everything happens in 200 words or 200 characters only. So shortest possible time, say something. That is the most challenging thing. So speakers have done a good job. And of course, the third thing that we talked about was the challenges in the storage of hydrogen. Of course, all the speakers have given a very good, insightful thing to us. In fact, whenever I think about the energy front, I remember this story of Birbal ki khichdi. So there's an energy source and the khichdi is somewhere else. So actually in the energy front, what you need is that energy should be there at the point of usage. So when we are transporting things, so the easiest thing that comes to our mind is electricity, which we can transport to anywhere. One of the modes of transportation, and it's very easy to use, very convenient to use. But what do you do with the time skew? If you have energy which is generated in the daytime, you cannot store it for the night time. So that is wherein these EVs and hydrogen comes up. So I hope that this hydrogen thing is going to stay. We have really borrowed the environment from our children. So I hope things improve. The green hydrogen is going to stay. And this mission hydrogen is in a very, full step ahead with the ministry also. Dr. Venugopal will agree with me that Center for Excellence, I'm a co-member with him in that party. And then there's also one meeting which was being done by MNRE today also. They were into the development of what is the standards and the regulatory forms that are, they are going to have a meeting on the 8th of May. So these things are there and the government is full step ahead going with this mission. So thank you all. And thanks Dr. Venugopal for giving me a chance to come over here and chair this session. And thank you Indian Oil and of course the other organizers also, IIChE-BRC, and thank you all the speakers. Over to you, Basim.
Thank you, sir. As a token of appreciation and remembrance, I would like to request panel chair, Sir Ashish Bhushan, to present memento to Sri Nitin Jansari. Thank you, sir. I would request panel chair Sri Ashish Bhushan sir to present memento to MS Pooja Shah. Thank you, sir. I would request you to present memento to Sri Santosh Radhakrishnan, sir. Thank you, sir. I would request you to present memento to Sri Somnath Sarkar, sir. Thank you, sir. I would request you to present memento to Naveen Jain, sir. Thank you, sir, for conducting and concluding the technical session 2. We are grateful to you for your effective moderation of the session and for sparing your time to attend this session. As a token of appreciation and love, I would request Sri Dharmesh Pancholi to present memento to Sri Ashish Bhushan, Director, Process and Engineering, OISD. Thank you. And with this, we are concluding our day one of National Conference Connecting Green Hydrogen to 2024. And I have an important announcement to make. We have 2 buses arranged for reaching to the venue of our musical night and dinner program. So you can avail this facility. We have an arrangement of 2 buses outside. And we also have an arrangement for rickshaws for the delegates who can, reach out to their homes if they want to, and they can avail that facility too. And we will be starting our day 2 tomorrow at 9:30 a.m. sharp. And our breakfast would be there for morning 8:30 to 9:30 a.m. So yeah, with this we are concluding. Thank you for your attendance, and we'll see you at the dinner menu. Thank you.